Okay, dear participants, good evening once again. And our today's resource person, as this is day 3 of this 6 days ATAL online FDP, Dr. Umakant Nanda sir from VTAP University. He has already joined us. So we will go ahead with our session right on time. Umakant Nanda sir, good evening sir and welcome.
Very good evening, sir. Thank you.
And you have been made as a presenter. So after a brief introduction, you can share your screen, sir. You have been given screen share option also.
Sure.
Umakant sir.
Yes, sir.
Yes, sir. We will start now.
Sure.
So again, a very good evening, my dear participants and the respected and distinguished resource person, Dr. Umakant Nanda sir, Dean Sense VTAP University. And before sir proceed with his session, I would like to invite our co-coordinator, Madam Dr. Y. Arpita, to give a brief introduction about today's distinguished speaker for session 5. Madam.
Sir, am I audible, sir?
Yeah, audible.
Okay. Good evening, everyone. It gives me great pleasure to welcome you all to the third day of AICT ATAL sponsored FDP on advanced VLSI design and AI-enabled automation for next generation semiconductor manufacturing. After a highly insightful and engaging 2 days of FDP, we look forward to continuing the momentum with another enriching set of sessions today. We are deeply honored to have Dr. Umakant Nanda sir today as a distinguished speaker of this session, Professor with AP University. I take the privilege of introducing Dr. Umakant Nanda sir. Dr. Umakant Nanda has received the MTech and PhD in Electronics and Communication Engineering from NIT Roorkela. He is currently working as Professor and Dean of School of Electronics Engineering at WIT AP University. He has more than 15 years of teaching and research experience in different education institutions. He has guided more than 20 UG and PG student projects. 5 PhD scholars have got their doctoral degree, and another 8 scholars are working under him in areas like analog and mixed signal integrated circuits, beyond CMOS devices and circuits, application-specific processor design, and embedded systems design. He has published more than 110 research papers, including reputed SCI and Scopus Index journals, conference proceedings, and book chapters. He is also the co-inventor of 6 patents which have been published. He is a senior member IEEE, IETE, a life member ISTE, and a member of IEEE EDS Hyderabad. He has successfully conducted many workshops, FDPs, STTPs, seminars, value-added courses, and training programs. He was the convener of 2nd, 3rd, and 4th International Conference on Artificial Intelligence and Signal Processing, sponsored by IEEE in 2022, 2023, and 2024, respectively. He is also the convener of 5th International Conference on Advanced Distributed Computing and Machine Learning, organized in 2024. He has worked as reviewer and editor of numerous journals and conferences of international repute. Sir, we are deeply honored to have you as a speaker for this session, and I request you to hand over the sessions. Thank you.
Thank you, madam. First of all,
Thank you, sir.
very good evening to all the participants present here. And I would like to thank Dr. Srinivas to invite me to be a resource person in this ATAL FDP for 6 days. Now, I'm going to share the screen. Just a second. Hope the screen is visible to all of you.
Yes, sir, visible.
Yes, sir, visible, sir.
Okay. So thank you again. So we'll start the talk now. So this talk, as the organizers have mentioned, it will be going on totally for 1.5 hours. So my talk will be for 1 hour and 15 minutes, and another 10 to 15 minutes we will have the discussion. So let me start with the topic. As it is mentioned, nanowire array-based gate-all-around MOSFET design for future generation memory devices. So first of all of you, most of you know that what is a MOSFET. Okay, so metal oxide semiconductor field effect transistor. All of you know it. Then what is preceding with it, that gate all around? What is that? Okay, so first of all, you know what is gate. You know what is the meaning of all around. All around means it is everywhere. Means around the some device it will be there, right? So gate will be around a particular material or particular device, it will be there, right? So why it is needed, that we will discuss, and what is the problem with MOSFET, that we will discuss, and how this type of devices can be useful for memory devices, especially why that is required, and in the memory devices what is needed, and why this particular device is important for memory device designs. So those we'll discuss one by one. So my presentation outline will be in this manner. First we'll see the introduction of the MOSFET and the primitive devices after the MOSFET, what were invented, and nowadays what we are doing. All those things we'll see. Then we'll jump into the nanowire gate all around MOSFET design. And in that, what are the recent developments we have seen, that we'll see. Then what is the motivation behind this research? And what are the objectives, and what are the methodologies of this particular device research. And basically we'll discuss about 3 problem statements. So what are those problem statements? First one is the cylindrical GAA silicon nanowire MOSFET multi-gate design. Second one is analytical model of multi-channel, that is the word you should understand, multi-channel nanowire GAA for electrostatic performance improvement using high K dielectric. Then third one is to design a novel model named nanowire array based. So array based GAA MOSFET. Array based means there are multi-channel will be shown as an array of channels. Okay, so that we'll see for a GAA MOSFET, gate all around MOSFET. And then we'll see what are the conclusions and what are the future scope of research. Just let me go with a laser pointer. Okay. So coming to the introduction. So first of all, what is the MOS device and what is the problem with it? So that we are going for beyond the MOS devices, different type of advanced devices we are going for. What is the problem with it? So see, when the MOSFET devices are scaled down continuously over the past 4 decades, this is being happening. Scaled down continuously means the size of the MOSFETs are being scaled down. It is minimized. Okay, due to this miniaturization, so the device size will be decreased, and because of that the higher packaging density will be there, and also the speed of the particular circuit or particular system will be more. Definitely always we need VLSI means what? 4 things. One is the speed of the device, then what is that the area of the device, the power consumption of the device, and the cost of the device. Always you remember VLSI we are talking about means these 4 things we will always see. What are those? Again, I am telling, that is speed, power, then area, and cost. Cost also it is important very much. Okay. So all these things can be achieved if the size of the MOSFETs are scaled down. Okay. But while scaling down the MOSFET size, what will happen? There will be some unwanted short channel effects. What do you mean by short channel effects? So first of all, what is channel? You know what is the channel? The area in between the drain and source of a MOSFET is called as the channel, through which the electrons will pass, and we are getting the drain current for that, due to that. Okay, so that channel, if it is being shortened, some short channel effects will be coming out, like drain induced barrier lowering, like punch through effects. Okay, many effects will be coming because of reducing the channel length between the source and drain. Okay, so that will happen when with the planar MOSFETs, like regular MOSFETs. What are the MOSFETs we are seeing in our BTech level or MTech level we see? But due to these effects, these are the unwanted effects, and we have to reduce it. If we cannot reduce, then due to these effects, the MOSFET will give you the bad results, or the wrong results, wrong output. Okay, so that is why we have to come up with some new ideas, so that we can replace this type of MOSFETs with some other devices, right? So basically, the short channel effects reduction can happen by two things. One is called as the gate engineering. So gate engineering, the last sentence is written, you can see the gate engineering and the channel engineering. These are the two things we can do. Okay, we can do for possible alternative to replace the planar CMOS technology. So the MOSFET, planar MOSFET can be designed so that the gate of the FET can be modified, or the channel of the FET can be modified. So both of these things actually we are going to see in this talk. So how we are able to change the gate, how we are able to modify the device by modifying the channel also. Those things we will see it here. Okay. So first of all, what is the gate engineering that we will see? So gate all around the GAA, gate all around, I will tell now GAA now onwards. So please try to understand what is the GAA. Okay. So GAA device becomes a promising structure design by changing or modifying the gate. Okay. So if the gate will be modified like double gate, triple gate, multi-gate, gate all around. Okay, all those things coming into picture, so that the device will give us the promising results, like the ID current and the ion by I of ratios, switching ratios, sub threshold swing. All those things will be coming better. Second thing is that the channel engineering. So already I have told you the channel. If we will do something like we can go for multi-channel devices, like single channel. Always we see in the MOSFETs, single channel is there in between the drain and the source. But can we go for multi-channel devices? Yes, we can go for. If we will do that, then what will happen? The drain current will be improved because more number of channels will be there. The drain current will be improved, high switching speed will get, and the short channel effects also will be reduced. So this gate engineering and channel engineering, including both of these engineering techniques, a novel device that is called as nanowire array-based GAA MOSFET is designed in this particular research, and we'll see that how the device will be looking like and how the performance it is being improved. So definitely, yes, if we will do this channel engineering, we'll get a great electrostatic controllability over the channel. Okay, so that is what we will find, and due to that, the ID current also will be enhanced. High switching ratio, low threshold voltage also will be there. What is switching ratio? I-on by I-off. That is called as the switching ratio. What is I-on by I-off? I means that is the drain current. ID actually. So at the on state, what is the current value, and at the off state below the threshold voltage, what is the current? There will be some current that is called as the leakage current. So that leakage current, how much it is? What is the ratio between I on by I off? That is called as switching ratio. And always I on by I off should be more, so that the switching speed will be more, and it will be enhancing the switching performance in memory devices. That is why I have shown you the topic name is the next generation memory design. This type of switching ratio, if it is more, then next generation memory device, that is the memory devices will be good, because you know what is memory. Memory means it is nothing but reading and writing of ones and zeros in a particular cell, memory cell, like a SRAM cell will be there. Okay, so in that how effectively or how fast the one or zeros are being read or are being written, that is what depends on the switching ratio. If the switching ratio is high, always that speed of that reading and writing in the memory cell will be good. So that is what is required, and also low threshold voltage. So low threshold voltage means the VT. If low threshold voltage will be there, then the I of value will be less. So that is what also we always think of. If threshold voltage will be low, then I of the off current will be less, and due to that again I on by I off ratio will be more. So what are the recent developments has been done in the MOSFET and different type of advanced devices? So look at here in this diagram, figure 1. So in the figure 1, first we'll see we see that conventional MOSFET, all of you know in our BTech and MTech level, we have already learned about the conventional MOSFETs, which is having 4 terminals, that is gate, drain, source and body, and there is a single channel, and that channel will be going through the inversion, accumulation, all those regions it will go through, and finally we will get a drain current, all those things you know. Then what happened in this diagram figure 2, you can see from the left side, first is the conventional MOSFET. Second one, you can see in the both the sides, top and bottom, there is a gate. You can see S and D are the source and drain. Top and bottom are the gate regions. So there are 2 gates here. Compared to the first one is a single gate. Second one is 2 gates. So that is called as double gate. So if double gate will be there, the control over the channel will be more. See, if we are taking one hand and we are holding something we are holding like a stick or a big stone we are holding. If we will hold with 2 hands, what will happen? The control over the structure will be more. That is what it is happening here also. The gate, if both the gates will be there, the control over the channel will be better. Okay. So that is what needed. What is the control? Control means what? The channel, in between the channel, what are the electrons are flowing, that should flow only from source to drain. They should not go here and there. Okay. So that is what will happen if double gate will be there. Then what comes in the third one, you can see triple gate. Triple gate, that means at the top one gate is there, at both the sides one gates are there, so it is called as the triple gate. So it will have more control. Then what happens? Next one is fourth one, the last one you see, this is called as a gate all around. What is gate all around? So around the channel from source to drain, you can see around the channel the gate is there. That means 4 sides, 1, 2, 3, 4. So 4 sides the gate is there. So this is what called as gate all around. Okay. So this gate all around will give more control on the channel. Then another type of device is also there, FinFET. So FinFET, you can see a fin-like structure. So fin-like structure will be there as a gate. So that is the 5th one. Then in the gate all around, in the gate all around section, we will have another one which is called as the nanowire gate all around. Nanowire means there is a wire-like structure. See, what is the difference between this 4th structure and this structure? You can see both the sides, drain and gate will be there, drain and source will be there, but it will be a wire-like structure, the circular structure. Okay, that is called as gate all around, but nanowire. So wire-like structure. This is a rectangle structure. Here, this is a wire-like structure, circular structure. This is what is the best one, and we are going to talk about this. It is best in the form of the ion by IOF ratios, as well as it will be the threshold voltage will be less, gate controllability will be more. So that is why this we have taken for our particular research, and we have seen this is giving a very, very good result in the form of the device requirements. You can see here this particular device we have shown here, like you can see left side source is there, right side drain is there, in between the gate is there. Okay, so source and drain are in the blue color, you can see left and right. In the green color, the metal is there, that is called as the gate. And after the gate, the insulator is there, that is gate insulator. That is we generally take it as the oxide, that is the silicon dioxide SiO2 layer we take. Okay, but people are taking also other particular oxides that we will see in some work we have done that also. So generally we take SiO2 layer under the metal, then the channel will be there in between source and drain, and the control can happen from the metal side. Okay, so from the metal side, definitely that control will be there. Okay, so here you can see the metal or the gate is all around surrounding the particular source to drain channel. Right. So This is what called as nanowire. Nanowire all around, gate all around MOSFET. So our motivation for this research, already I have discussed, is that the long channel and the short channel is will be definitely having the effects. The short channel effects will be there. Long channel means generally we go for, suppose you people might have used the cadence, and in that cadence you are using the technology. Maybe it is 90 nanometer technology or 65 nanometer technology. So what is the technology? That is the channel length. So in that channel length, what is the channel length? That 90 or 65, or suppose it is more, that is 135 or 180 nanometer, and more than that also is there. So more than 65 or 90 nanometer, it is called as long channel. If we will go for less, that is 45 nanometer, 28 nanometer, nowadays even 5 nanometer or 2 nanometer technology also we are using nowadays. That FinFET technology is being used by Qualcomm. So they are using less, very less technology size. Okay, so those are the short channel. And if you will go for, have you seen the MOSFETs of 5 nanometer technology or 10 nanometer technology? No. So MOSFETs will be definitely will go for minimum 65 nanometer. Then only you will get a particular result, whatever required. Otherwise, the results will be wrong, and we cannot rely on that device. So basically, the digital logic, for the digital logic applications, the scaling challenges, that is the short channel effects, will be coming more. And this reduction in short channel effects and increase in drain current with low supply voltage is very much needed. So that is what our particular motivation for this work. The electrostatic controllability over the channel is very much required by the gate, and the driving capability of the GAA MOSFET should be better, and that can be improved by channel engineering techniques. Channel engineering means, again I am telling, multi-channels we can go for, or the channel length, or this one, the width of the channel, thickness of the channel, those also we can vary to see whether the results are coming better or not. So our objective of this particular work research is like this. As I have told you, cylindrical gate all around MOSFET design using Synopsys Central Sticker tools. So Synopsys tools is a very good tool. So what we are using in our lab, it is available, and I also I can tell all the participants here that you can go for Synopsys Central tools, which is available, and it is being availed by different institutes, and it is being given by the government of India, that is from the MIT, it is being given. So if it is not available, you can please get it from them. And this is very reliable software, Synopsys Central tools. Even other tools are available, like Silvaco is also available, Console is also available. You can do those things there also, very good software. So Synopsys Central is also very good. So we have designed this particular work in Synopsys Central tools. Then we have gone through the position dependent multi-channel GAA MOSFET. What is this? So multi-channels will be there. So channels will be like this: channel 1, channel 2, channel 3. What is the distance between each channel? If we will vary those distances, there also we will see some variation in the drain current and other factors also. We'll see that. Okay. Then the array based 2 or 3 channels, it is fine. Then if we will go for 9 channels, 13 channels, or more than that, that is called as array of channels. Okay, so that nanowire array. So channels are looked as nanowire and array based GA MOSFET. How to design and how to see these results, those are also in the picture. We'll see it. Okay, then we can go for a drain current model also, where we can use the high K HFO2, or HFO2 means hafnium oxide dioxide, and silicon nitride also we can use as a high K dielectric. And if we will use that, then again the results will be coming better. And finally, we will see one in SRAM applications how we can use the device. This is the methodology, basic methodology for this research. You can see first we will see go through the literature review. Literature review means what have been done already in this particular device or similar devices, like we have seen in one of the slides. First, we have gone through the double gate MOSFET, then triple gate MOSFET, then gate all around MOSFET, then the nanowire gate all around MOSFET. All those things in the literature review, you go through the good journal papers. There you see what is available and what is the current work is being done. Then from there you can come up with your own idea and you can go for your particular design. Then what is the next step? Design requirements for basic device. So what is your performance requirement? So what should be your on current? What should be your off current? What should be your ratio, current ratio? What should be the switching threshold voltage? And what should be the sub-threshold swing? All those things is required to know first. Then you will go for design. Then come to the design of multi-channel GA MOSFET with high K dielectric. So as we have seen in the last slide, what are the high K dielectrics? Those also if you will use, then better results can be found. Then analytical model for drain current, that drain current equation for your work you can go for. Then you can go for the design of a novel model name, that is nanowire array based, means number of channels will be more than 3, like I have told 9 or 13, like that also you can go for. Still a better result, better ID current, on current will get. Then the device performance parameters will be determined and we'll see whether it is matching to our requirement or not. Okay. Then if it is matching, then go to the solution. That is what the solution will find. Obtain the solution. Then you see that results will be can be interpreted in the form of some applications. Like take the example of memory application or any digital logic applications, you can put it. So that is the application part finally. So this is the complete research methodology. You should go for any research, not only in this area, particularly any research if you'll go, you should go through this particular flow. So starting with the background study to the application. With this research, we have come up with a publication. This publication was done in 2021. This is actually one of my PhD scholars' work. That is what I am presenting here. So, so she was K. Bhol and myself. So this was the publication we came up with, SCI journal paper, recent patents on nanotechnology. Here we have reviewed all the papers, previous papers, what was done in this area. And then we have gone for this review paper. So that was our first problem statement, the comprehensive review on literature survey that already we have seen. Then with that review, see, if you will go through many papers, then you will come up with the real problem statements. The real problem statements, what we have seen. So, and we have gone for those work also. So first is problem statement number 2. Design of cylindrical GA MOSFET where a single channel will be there. Then second one, multi-channel with two channels. I will show you how 2 channels will be there and they are position dependent. Means if the channels will be separated by more distance, what will happen? If they are close to each other, what will happen? And the effect on the device performance. Then we will come up with the multi-channel, like 9 channels or 13 channels. That is the problem statement 4. Then we can go for another problem, that is coming up with a drain current equation, analytical equation. So that also can be there. So like this, you can come up with many problem statements after the literature survey. Then come to first work, what was done in this area, that is cylindrical gate all around MOSFET. Here multi-gate is written, but multi-channel is not there. There is a single channel that we will see. Okay. Look at here, these structures. very good looking structures are there. These are also the field effect transistors and MOSFETs itself, so called as GAA MOSFET. So here you can see in the A, figure 3A, here left this side source or drain, this side source or drain, in between the gate is there, and below that gate the oxide will be there and channel will be there. Okay, so this is one type of structure. Then what happens, this B structure, you can see what is the difference between these two. So we should not go for the gate length more. We have reduced the gate length here. Okay, the length of the gate has been reduced, but the channel is there. You can see the channel is there, that much size. Okay, gate length has been reduced. The width of the channel is also reduced here. Then width of the channel is there, C structure, you can see, and the gate is having that much length, that is C. But the D, you can see 3D, this structure. What is there? What is the difference between all other structure and this structure? Is that here three types of metals we have taken, M1, M2 and M3. So this is called as multi-metal structure or multi-gate structure. Okay, so multi-gate structure, you can see back to back different type of, due to the colors, the type of gates can be changed, and multi-gate, it can be told as the multi-gate structure. Okay, but single channel only. Channel is a single one in all these four structures. Then come to this slide, you can see, as I was telling you earlier, there is a two type of engineering called as gate engineering. Second one is channel engineering. Due to these two type of engineerings, we can go for various device designs and we can come up with better results too. So first one is gate engineering. What is the meaning of gate engineering? These three things can be done in the gate engineering. That is, first one is the length of the gate, LG. LG means length of the gate can be varied to get better result. We'll see that in our simulation results also. We can see that metal gate work function. So the work function, that is phi m, the gate work function. Okay, so that can be varied. If that will be varied, then what will be the result? How it will affect the results? Then metal gate underlap and overlap. Okay, so the gates, suppose M1, M2, M3 are there. Are they overlapping or underlapping with each other? So that also you'll see. And if they are underlapping or overlapping, what is the length that they are underlapping? There is a chance while doing the while going for the device fabrication, then the underlapping or overlapping may happen. If that is happening, then how the results it will vary. Then come to the channel engineering. The channel engineering, two things we can see. There is a channel. There is a channel means the thickness of the channel can be varied. If the thickness of the channel can be varied, as we have seen in the last slide, you can see the channel. This is the channel. From here to here, channel is there. The thickness of the channel, you can see this can be varied. Here thickness is something, here thickness is something, here thickness is some other thing. So if the thickness of the channel is being varied, how the results will be changing, that we will see. And the doping concentration in the channel, that also if we will vary, then how it will overall results will be varying. So these things are coming under gate engineering and channel engineering, right? Now you can see the gate, only gate it has been shown here in this diagram. You can see in between channel is not there. There is a hollow. There is no channel. Only the gate is there, right? So in this gate, what is the gate length? You can see LG, length of the gate, that has been shown here. Okay, so if this length of the gate will be varying, then what will happen? So length of the gate means already always you know the length of any MOSFET is at the denominator while calculating the ID current equation. Okay, so if the length of the gate will be less, then definitely ID current will be more. Here also same thing is happening. You can see the length of the gate has been varied from 10 nanometer to 50 nanometer. 10 nanometer to 50 nanometer. Okay, and due to that, how the drain current is being varying, you can see. So this is the x-axis is the gate voltage, drain current is in ampere it is showing, but 10 to the power minus 10 minus 9 like that it is showing. Okay, so it will be around micro ampere. So you can see at 50 nanometer the gate length, at 50 nanometer gate length, at threshold voltage suppose around 6.6, we will see what will be the value of the drain current. So it will be coming around 10 micrometers. Sorry, microamperes. Okay, so at 0.6 threshold voltage, that is the gate voltage 0.6, that is the threshold voltage suppose. Okay, then at that time we'll see the current will be 10 micrometer around, microampere around. Okay, so this is how we have changed the gate length and we have seen the drain current finally. Here we can see the work function variation also. The work function, see the work function for the gate of the PMOS and the NMOS are different. Okay, so you can see the for the NMOS it is around 4.1, okay, 4.2 to 4.6 around like that, and for the PMOS it is around 4.9 to 5.3, something like that. So this is the best work function. If we will take, then we'll get the best result also. So that is what we have seen it here. We have changed the work function, right? For N channel, left one is the figure 7 is for the N channel and figure 8 is for P channel gate all around MOSFET, where the work function has been changed from for the N channel 4.2 electron volt to 4.6 electron volt. The work function has been varied, and due to that you can see how the drain current is being varied. So if the work function is less, definitely the drain current will be more, and if the work function is more, then drain current will be less. So this simulation study has been done here while taking the VDS value, drain to source VDS value is 0.5 volt, and thickness of the channel, that is also there. Thickness of the channel has been kept constant, that is 10 nanometer, and thickness of the oxide, okay, that is also has to be taken, that is 2 nanometer we have taken. So these values have been kept constant both for N channel and P channel, you can see, and we have varied the work function value, that is 4.2 to 4.6. Similarly, for the P channel, you can see the work function value has been varied from 4.4 electron volt to 4.9 electron volt, right? So here also, as it is P channel, the 4.4 is the lowest one, the lowest drain current we'll see, and 4.9 will get the highest. So that was about the gate. Okay, so till now we are discussing about the gate. Length of the gate has been changed, work function has been changed, and the ID current we have seen. Similarly, come to the channel now, right? Channel engineering, already I have told you, thickness of the channel has to be varied. Okay, so what is the thickness of the channel? You can see here. The radius, the diameter of the channel is called as the thickness of the channel here, right? So with this thickness variation, you can see the thickness has been varied from 6 nanometer to 12 nanometer here. Thickness has been varied, and we have seen the drain current at the y-axis for different gate voltages in the x-axis. Okay, so here the thickness for less thickness of the channel 6 nanometer, definitely the current is less, and drain current will be more for 12 nanometer thickness of the channel. But see, we have to take the optimized one. We cannot see definitely the thickness will be more means definitely the drain current will be more. But what is the optimized value? That we have to see, because there is a, if the thickness is more, then the channel thickness, if it is more, then the device size also will be more. Can we go for more size? No. So we have to see optimized, and there is a definitely trade-off in between the thickness and the drain current. Okay, so that we have seen, and where VDS has been taken 0.5 volt, LG gate of the length is taken 50 nanometer, and the oxide thickness has been taken the as 2 nanometer here. Similarly, here we have seen the thickness of the channel has been varied as 10 nanometer, 15 nanometer and 20 nanometer, keeping constant the gate length as 28 nanometer. Okay, and the two metals we have taken here, first metal work function is 4.6, second metal work function is 4.4. So this is called as what? The gate, two number of different gates we have taken it here. So that is what we have seen, and keeping VDS as 50 millivolt constant, then we have seen the result, how the drain current is coming out. So this is called as double gate all around. So double gate, DGAA, that means double gate, and different work functions of the gates has been taken here. We were talking about channel. So next thing, the channel doping concentration. So see here, the doping concentration around the channel, across the channel, how it will be. Towards the source, the doping concentration will be around 1 into 10 to the power 20. Okay. And the doping concentration around the channel will be almost 0, and around the drain again 1 into 10 to the power 20. So like this, the doping concentration will vary from drain source to drain. So along the distance, the doping concentration are varying. Okay, and due to that varied doping concentration, okay, so here we have seen if the doping concentrations are being varied from 10 to the power 14 to 10 to the power 20 on the channel, in the channel I am telling. Okay, so here if it will be there like that, then how the drain current is being varied with the gate voltage. See here, here also we have seen what is the doping concentration. The values has been mentioned here. From red to blue, it has been shown here. So that was our first work that is called as the single channel, right? So now we'll go to multi-channel gate all around MOSFETs. So what do you mean by multi-channel? Why we are coming for this? So these are the things, the advantage we'll get here to improve the ion by I-off ratios. That is called as the switching ratio. Okay, so ion. If the device is on, what is the current? And if the device is off, that means the voltage, input voltage, gate voltage will be less than the threshold voltage. This off current will find due to the leakage current. And what is the ratio? That definitely we should always see for any digital applications like the memory cells. Then high current drivability. That means the gate should have good control over the channel so that good amount of current can be driven by ID, the drain. Then along with this multiple channel engineering, multiple channel based GA MOSFETs, also known as silicon nanowire GA MOSFETs, that is what our aim is, are getting developed as next generation semiconductor devices. So for the single channel, we have designed and we have conducted huge research on that. Then we have come up with a good publication for this, another SCI publication done by my scholar only, that is in the Silicon Springer Journal, SCI publications on that work. So multi-channel, when we are talking about, then the channels are position dependent. What do you mean by position dependent? As I have already told, two channels will be there. If the separation between the channels is varying, then the result also will vary. If that is there, then how these are varying, that we are going to learn here. Look at here. So what is this? Left side A is nanowire MOSFET, where you can see the cross-sectional view. In the cross-sectional view, the channel is having the silicon. This is a semiconductor. Silicon material will be there at the center. Then two types of oxides are there, or you can tell dielectrics. Okay, first one is Si3N4, silicon nitride, and second one is HFO2, Hofmannian oxide. These two types of layers are there in the yellow color and the gray color. Then after that, the metal is there all around. Okay, this is what the cross-sectional view. If you will take the cross-sectional view at C3, you can see, then will be seen like this. Similarly, if the horizontal cross-sectional view if you will take, then the structure will be looking like the C. The 14C figure, you can see there is the channel in between the source and drain. Then the high K dielectric materials like Si3 and 4 and HFO2 will be there. Then above that, gate is there. Okay, so this is how the cross-sectional views will be looking like. If we'll take like this, you can see what is the difference between the previous one and this one. Suppose I will take the B one. What is the difference? So in the B, you can see there are two different channels. In the channel region, how many channels are there? You can see two. Two channels are there. So that is called as multi-channel. If two channels will be there, then definitely the driving current will be more, the drain current will be more, and due to that we'll get a good advantage on ion by I of ratio too. Okay, so if channel 1 CH1 and CH2 are there, how the result will vary and how better the results will get, that we will see in this work. Look at here, as I was telling you, the separation between these two channels, channel 1 and channel 2, here it is 6 nanometer. So 6 nanometer is the distance between the center point of channel 1 and center point of channel 2. Okay, and what is the length, the thickness of the gate, that is 8 nanometer. Here you can see. Similarly, here the separation is 9 nanometer. And from the center of the device, our proposed device, from the center, what is the distance from the center to the oxide? Like this is 16 nanometer, then this is 18 nanometer, and this is 26 nanometers. Okay, and the metal work function, what is the metal we are taking? The work function is taken as 4.7 electron volt. Okay, so this is what another structure. Then another structure is there, channel 1 and channel 2. The separation is 10 nanometer. So three types of separations are there: 6 nanometer, 9 nanometer, and 10 nanometer. So all these things, other things have been kept similar, same only in all the three structures. Just this separation you can see 6 nanometer, 9 nanometer, and 10 nanometer. If it is there, how the result will vary. Look at here. This is the electrostatic distribution, electric field distribution. In the channel region, definitely it will be more, and others in the blue color. So electric field distribution will be more in the channel only. So these two channels are there. Yes, the separation is different. Here the separation is less, here the separation is more, and here still more, 10 nanometer here. And in this proposed device, we have taken the channel length. Till now we are talking about the thickness. So channel length 20 to 60 nanometer we have varied. Then doping concentration, that is the intrinsic doping and donor, that is taken as 1 to the 1 into 10 to the power 20. Then doping concentration from the acceptor and donor, then that is taken as 1 into 1 to 10 to the power.
Yes, sir. 1 second, sir. Channel length is LG or gate length LG? In this table, channel length within the brackets LG is written. Is it correct?
Yes, it is a gate length, sir. Gate length, not channel length.
Yes, okay.
So gate length is taken as LG, that is 20 to 60. Then oxide thickness, different oxides we have taken as the dielectric material. So there also thickness is taken as 16 nanometer, 2 nanometer. Then channel thickness is taken as 10 nanometer. And source and drain extension, that is 20 nanometer. Means both the sides will be there other than the channel region, 20 nanometer, both sides we have taken. And after taking this, we have seen the results are coming like this. So what are the results? There are 4 different tables. We will try to understand each one of them. So first one is device performance for different channel separation. Okay. So what is the channel separation we have taken in the last slide? That is 6 nanometer separation, 9 nanometer separation, and 10 nanometer separation. Due to that separation, keeping constant the VGS, VDS, and gate length like this, we are getting the ion, I off, and ion by I off, and threshold voltage and sub threshold swing. Okay, so ion by ion is getting we are getting less in the if the separation is less, and ion will be more in the if the separation is more. So 10 nanometer we are getting a better ion, best ion, and the I off is also varying from 6 to 10 nanometer. And but always we have to see this one. This is very important. Ion by I off. If this is coming better in which one, that only we have to take. So it should be more. Okay, it should be more. So what is the value we are getting here? It is high. 9.13 into 10 to the power 8. We are getting here ion by I off. See, this is called a switching ratio. This should always be very good. Due to that, the reading and writing capability of the SRAM cell will be coming better. That is what is very important. Then threshold voltage is also very important. It should be low. What is coming in the first one only, that is a separation of 6 nanometer. That is very good we are getting here. And but you can see sub threshold swing. So what do you mean by sub threshold swing? So sub threshold swing means in the sub threshold region. Sub threshold means below threshold voltage region. The MOSFET current, the drain current is getting varied. Okay. So what is the variation? For decade drain current variation, how much voltage is required? Gate voltage is required. Okay. So that is called a sub threshold swing. Again, I am telling for the decade current variation, ID current variation, how much gate voltage is required, right? So that is what called as the sub-threshold swing, and always it should be less. If less gate voltage is required for more increase in the drain current, that is always better. So here you can see it is coming better here, the last one. So there is a trade-off in between the VT and the sub-threshold swing. Then comes different figure of merits of the proposed device for a channel separation of 6 nanometer. So now we have taken in these three next tables, we have made constant the channel separation, that is 6 nanometer here, 9 nanometer here, and 10 nanometer here. Due to keeping this constant, we have varied what we have varied, the VGS we have varied, VDS we have varied, and the gate length we have varied. Okay, so here VGS is 0.7 volt, then 1 volt, then 1.5 volt we have taken. Then VDS also 0.5 volt. VDS is kept constant, and gate length also we have constant only. These are not varying, only VGS we are varying. Due to that, how the ion, I off, and ratio, and VT, threshold, sub-threshold swing, those are how those are varying. Those have been studied here again. Similarly, for the 9 nanometer and 10 nanometer also we have studied. Then due to this gate engineering and channel engineering, what we are getting as the transfer characteristic, that is the drain current versus gate voltage, that we are getting it here. Okay, so the graph has been shown here. Next one is the transconductance. What do you mean by transconductance? The output current variation due to the input voltage. Okay, so that is del ID by del VGS. So due to the gate voltage variation, how the ID current is changing, that is what it is showing here. See, when it is changing around in between 0.5 to 0.6, it is increasing, or till 0.7 it is increasing. Okay, so the drain current, it basically from 0.5 it is increasing till 0.7 and more than that also. Okay, similarly here the change of ID current is very high here. The change, it is very high here at around 0.6. It is very high, right? And then it is the change is getting lowered towards down. That is the drain current variation is in the negative side. Okay, that is what the transconductance we are getting it here. And also we are getting the transconductance, change in transconductance versus change in VGS, the gate voltage. That is also we are getting here around 0.5. It is very high. Then it is getting down. It is depending on this figure only. So that is what it is getting down. Again, it is coming to constant. So previously it is constant, then it is changing, then it is getting constant here. So where we are getting the highest value, that is around 0.55 or something like that. Okay, so that is the threshold voltage. We will see that as the threshold voltage 0.55, 0.6 in between that. Then due to that, we are coming up with another paper, journal paper. So this is the position dependent multi-channel GA MOSFET. It was published in Journal of Nano and Electronic Physics. So it is a Scopus Index journal published in 2022. Then this is another work which we have seen here. You can see nanoware array based. So till now we have seen how many channels? 2 channels. Okay. What is the separation between those channels? And due to that separation, what is the effect or how the drain currents are being varied? That we have seen. Now array. Array means number of channels are more. It is not restricted to 2 or 3. It is more than that. We have taken 9 channels or 13 channels like that we have taken here. So this design, this is also channel engineering, right? So this design is done in 2 different ways. What is those 2 different ways? You can see here minutely. So each channel is having its own oxide here, oxide layer, right? So this is having its own oxide layer. This is own oxide layer. This is also own oxide layer. Pink color and gray color. You can see pink color is the channel and gray color is the oxide layer. For each channel, one oxide layers are there. This is how the nanowire rods, you can see it like this. Okay, these are called rods or pillars, whatever you can tell it as. But here what is happening? Second one. And the second one here, the channels are there, but for each channel, oxide is not taken. There is a common oxide where the channels are there. The oxide is in gray color. You can see it here. And the channels are there. Each channel oxide has not been taken here. Okay. So these are the 2 different arrays. The has been arranged in this particular channel region. Here you can see 2 types again. Here a circular way of arranging the channels and a square way of arranging the channels. 2 different ways are there. So this is called a square way. This is called a circular way of arranging the channels. That is also different types we can see, and we can do the study on that, and which is giving better result, that we can see it in this. So these are the 3 type of structures. One is circular way, structure 0. Structure 1 is each one is having its own oxide. So structure 2 is it is square, but each one is not having the oxide. It is a common oxide present throughout the channel region. So these 3 type of structures we have studied, and due to that, by taking those structures, we have done huge research on that, and we have come up with the results. Which one is giving better results? We'll see it here. So again, the on current, off current, switching ratio, threshold voltage, and sub threshold swing has been measured for different structures. Structure 0, 1, 2. So on current is coming in structure 0, it is very less, and structure 2 it is more. Off current, it is very less in the structure 0, structure 2 it is more. But what we have to consider? We have to consider switching ratio, where it is coming better. So switching ratio is coming best in the structure 1. Among these 3, structure 1. Structure 1 is what? Structure 1 is this one. where the oxide thickness is there, oxide is there for each channel. Okay, so switching ratio is coming best here, structure 1. Threshold voltage is coming best in structure 1 only. Okay, and subthreshold swing also coming best in the structure 1. So structure 1 is the best way of arranging the channels. That is what we have seen. But here, what we have seen, the oxide will be there for each channel, right? Then structure 1 only we have seen, as it is coming better, we have taken the structure 1 and changed the gate length. Structure 1, we have changed the gate length from 10 nanometer to 17 nanometer. We have changed and we have seen the switching ratio, which is coming 70 nanometer gate length. Switching ratio is coming best. Then the threshold voltage is coming best here because normally the gate length is less. So this is also very less here. And subthreshold swing is best in the where gate length is 70 nanometer. So then see any research on this device field if we are doing and we don't have any reference. What is the reference? The fabricated result reference. So fabricated result always we have to calibrate our work with a fabricated result. So here also we have taken a GA, gate all around MOSFET fabricated result. The third reference I'll show you that one in the next slides. So the fabricated device was there, gate all around MOSFET device was there, and it was the experimental data was shown. From that, the drain current, you can see the red color one is the fabricated result. Okay, so fabricated after fabrication, the experimental result is the drain current red one. It is there, which is there in reference 3, and our result is coming little better. And in line with that, you can see how the black color one is varying, and this is taken where the VDS value is 0.5 volt, the gate length is 100 nanometer, and silicon this one thickness of the channel is 10 nanometer, VGS is 1 volt, TOX the oxide thickness is 2 nanometer. So by taking these values as constant, we have changed the gate voltage and we have seen the drain current for our work, and their work is in the red color. Then this is also has been shown here, the gate voltage variation and the drain current variation are the y-axis. Then the transconductance also has been shown here in the y-axis with respect to the gate voltage in the x-axis. Then the electrostatic potential distribution has been shown here in the scale also is there. The scale is at the top side, red color is the highest, and then the blue color is the lowest. It is varying throughout the channel. And the drain voltage to drain current change also we have shown it here. These are the different electrostatic potential distribution for different proposed structures of the nanowires. For the different silicon pillars or the rods, how the electrostatic field distribution is happening. This is all generated from the this one Centers tools. So finally, this work, the array of silicon pillars, that by taking that, we have compared our work with the reference 8 and 10, which are also simulation works, and we have compared. Here in our work, mainly the subthreshold swing is 64, which is coming better than others, and VTH is also coming better than others. Switching ratio also 0.812 into 10 to the power 8. So that is coming better than the others. Little bit slight coming better than the others. Then this is a comparison of our basic device work. Basic device means only single channel was there, and here multi-channel we have taken. So the square structure. Multi-channel means the square structure where multi-channels are there. That also we have compared, and here also for this novel device, the sub-threshold swing is coming better, 64. Sub-threshold swing around 60 will be good. So it will be looking at a good result. Then this particular device has been used as a basic this one inverter. So the inverter in and out, V in and V out transfer characteristic has been, VTC curve has been shown here. Okay, so while doing this, you can see the circular arrangement and rectangular arrangement. Rectangular arrangement is shown as a red color. Circular arrangement is shown, the result is shown in the black color. Then it has been the NMS, the noise margin high and noise margin low has been compared with different reference papers 9 and 15 with our work. The propagation delay is also coming better here. That is the TP, propagation delay for this device, for this circuit. This inverter circuit has been shown here. So after that, this work was also published in Silicon Journal, which is the one another SCI journal, which is published in published as nanowire array based MOSFET for future CMOS technology to attain the ultimate scaling limit. This is the fabricated device on this array. So silicon nanowire array. You can see here, this is the fabricated device, and multi-channels are there. So 2 channels in each one, 2 channels are there. This one 2 channel, this is 2 channel. Actually different devices are there. This is one device, this is another device, and each one is having 2 channels. Okay. So this is what constructed by IMEC Belgium, and it was having 8 nanometer wide nanowires on a conventional silicon surface. So the material used was silicon only. Then we'll come to the conclusion as the time is also already there. So we'll come to the conclusion and future scope of research. So in this particular talk, we have discussed about what are the major problems with MOSFET, what are the short channel effect problem, and due to that, we should come up with the new devices. We cannot rely on only MOSFETs. We should come up with new devices like double gate MOSFETs, then FinFETs, then triple gate MOSFET, gate all around MOSFET. Then we have come up with this type of gate all around MOSFET that is called a cylindrical gate all around MOSFET, where a circular gate will be there around the channel. So here we have done 2 things. One is the gate engineering, one is the channel engineering. In the gate engineering, we have varied the length of the gate, double gate, double material gate we have seen, and 3 types of metals, M1, M2, M3, 3 types of metals we have used in the gate. Like that, gate engineering we have seen. Similarly, channel engineering means the thickness of the channel we have changed, and multi-channels we have seen 2 channels, and by separating the channels, how the results will vary. And more than 2 channels, if we'll see, that is array structure, if we'll take how the result will vary, that also we have seen. We have also taken the oxide or dielectric materials HFO2 and Si3N4. That materials also we have used to get a better result. Where we have used we have replaced the conventional SiO2 layer. Generally, in our MOSFETs, SiO2 layer we use, but in this device we have taken different oxide layers. Then So with this, the conclusion is that if we will take the multi-channel array structure, we are getting a very good switching ratio as well as the sub-threshold swing, so that we can use this type of device in digital circuits like inverters. Inverters we have seen, but similarly we can go for designing the memory structures also, memory SRAM cells, where 6 transistors will be there, and we can go for their performance calculations. Then if we will see, we can go for different type of other high-K dielectric materials that also we can see in the future work. We can go for some type of in the future work, we can go for some type of biosensor applications. Here we have seen only the circuit applications, but biosensor applications also we can go for using this type of devices. So these are the references. I was telling about this one. This third one is the device which was fabricated, and these are the other references we have taken. So with this work, we have published these 6 journals. Some journals I have shown, but other journals also we have published. Like the best one is the IEEE transaction on electron devices, was published in 2023, December 2023. Then other journals also we have published on this particular work. So yes, this is one of the work done by one of my PhD scholars. I am also working in different areas. Like I am working on the nanosheet MOSFETs, nanosheet FETs, okay, T FETs, and I am also working on solar cells. These are about the device and material part. My work is also being carried out on the circuit simulations on Cadence Virtuoso. The analog circuit design and mixed signal circuit design also I am working with. So currently 8 PhD scholars are working under me on these particular areas. Some other collaborated papers on this work, what was talked on today. So these are some papers also published, some book chapters, one conference. So these are some other journals. So thank you. Any questions, please? You can.
Thank you, sir, for a very nice session. Dear participants, now session is open for you. If you have any questions, you can ask.
I think the time is 7:20. Exactly, the time was maintained.
Yes, sir. Yes, sir.
Yes, sir.
Sir, good evening,
Sir,
sir.
one question. Okay, sir. Please go ahead. Please go ahead.
Good evening, sir. I am Murali.
Yes, sir.
So, may you know what are the limitations of the corporate when we are using multi-channel gates?
So
That means to be
limitation
used-
actually, yes, very good question. See, we can increase the number of channels, but there is a trade-off. Like I have shown the trade-off in between the subthreshold swing and the ion by IF ratio. Yes, subthreshold swing is coming better when the subthreshold voltage is better, but ion by IF ratio will be also coming into picture. So by taking the trade-off into consideration, we have to come up with the optimized number of nanowire rods. So there is nothing like we can always increase the number of rods, but always we have to see the optimized one, optimized result. Then only we should conclude there.
Sorry, sir. But if you keep multi-channels, the parasitic values are going to be changing. That's the reason only I'm asking that limitations.
Yes, yes, yes. There is oxide to oxide means cross connections will be also there. Due to
Yes,
that, parasitic components also coming into picture.
Yes, sir. My sense.
Okay, Umakant sir, there is a question posted in the chat by Naga Satyanarayana Murthy sir. That question is, I'm reading on their behalf, sir.
Yes.
Is a cylindrical GAFET supports the design the analog circuits like amplifiers and oscillators?
Circuit application will be there. It is supporting, see, if it is supporting for this this one as memory cells, will be there for analogs also, but we have not because that PhD scholar already left, already got passed from our university. We have not gone to that extent for the analog circuits, but I think for the oscillators, the voltage control oscillators, we can design. As per my knowledge, we can design because the analog circuits where the resistors and capacitors will be coming into picture. So how to convert this cylindrical GA FET to resistors and capacitors, we have to see that. But analog circuits can be designed as per my knowledge. Voltage control oscillators we can design. In fact, one of my scholar is working on this one, the nanosheet FETs. Nanosheet FET is this is also nanosheet FET, also gate all around nanosheet FET. But she is doing on the nanosheet FET. Using that, she is working on this voltage control oscillators, and that is working fine. Currently, she is working on that area.
Okay, one more question, sir, in the chat. How to overcome parasitic capacitances or resistances between parallel channels?
See, parasitic capacitance and resistance, how these are coming. That is what first thing we have to see. See, always if the gate length is being increased, then the resistance also will be there. Parasitic resistance will be there. So we have to see the trade-off there also. That is, if so much gate length will increase, then it is of no meaning. This parasitic resistance will be there, and due to that, the delay, RC delay also will be there. So that we have to see what is our specification, and due to looking at that specification, we have to come up with a particular device design. So that is what, as per the requirement, we have to see. That is why I told earlier, first we have to see the specification. What should be our delay? What should be our this power consumption and other things? Okay, and because of that, we should come up with a particular design.
Okay, dear participants. Okay, one more question, sir. What is the maximum speed of memory cell by using cylindrical MOSFET?
The memory cell, the speed that you are telling about this one, the reading and writing speed of the cell, that actually we have not gone through that. We have only done the transient analysis. So reading and writing, that we have to see that. This is just our main aim is to see the design the device, and using that device whether the memory cell is working or not, that we have seen. Other parameters, that also one of the future work we can extend that to the circuit level.
Okay, participants, any more questions? Sirs and madams.
Sir, one more. Sir,
Okay,
other
sir,
than
please.
circular channels, can we use any other shapes of the channels, sir? Like hexagonal shape of the channels?
That is a nanosheet FET is one of the design where the channels will be in the rectangular manner, as well as the gate also will be in the rectangular manner. That is nanosheet FET, different from this nanowire. Nanowire means it should be, wire means circular only, we will consider.
Okay, can we use other than that circuit?
Yes, yes, we are using, as I told, one of my another scholar is working on nanosheet FET. Yes, we
Okay.
can use that, and even in the circuit analysis also, she is doing that.
Okay, sir. Okay.
What is the tools? Tools, as I have told, this Centrus tool, the TCAD, Synopsys TCAD Centrus. So this tool is, yes, I should acknowledge the government of India also, who have provided the tools to us free of cost, and that the mighty Ministry of Electronics and Information Technology, they have provided the tools. So even not only Synopsys, we can use the other tools like Silvaco, that is also being provided. Then console also people are using. So different tools will be there you can use, but we are using the Synopsys Centrus.
Sir, somebody asking how does GA MOSFET technology? I think the question is not complete, sir.
No, I think he is asking this GA MOSFET technology is till what technology node? We have used till 10 nanometer. So that is working fine for us. And I think this one of the 8 nanometer, that is what I have shown for the fabricated result, that was of 8 nanometer. So that is the latest one. 3 nanometer I have not seen, but I might have missed also last 1 year. I have not seen on this particular work. So 3 nanometer maybe, but 8 nanometer definitely it is working. As I have shown one of the fabricated result, it is fabricated device. It was of 8 nanometer.
Okay, sir, one question from my end. What are the key challenges in fabricating cylindrical MOSFETs, nanowire MOSFETs?
Definitely the wire itself, that is the challenge. So while fabricating anything like silicon, we are taking the wafer. The wafer itself is not of cylindrical. It is a planar only. So there is the challenges, but we have the already this one is there. The fabricated device has been shown there. There will be some challenges, but it has to be explored. I have not seen all those things here. So in that paper, if it is required, I will send you. You can go through so that it will be seen there. But fabrication is being performed for this, as I have shown you one of the device fabrication.
Okay, sir. Before we close, sir, any suggestions from your end to the faculty which are at junior level, maybe from less than 5 years, to start their PhD in this field?
As most of them will be there as the MTech passed out, PhD they have not done. So this is a good area of research, the device research. Even not only this, the FinFET is there, TFET is there. So there are different challenges and which has to be explored. So if anyone is interested also, they can be in touch with me or with my research scholars. Definitely, they will help you also if it is required in your side. So this is one of the good area of research, and the getting the jobs also in the semiconductor market. It will be very good if you are doing good research here. Layout structure, we have not done anything on that till now. Just simulation work on the devices, device to circuit simulation only we are doing. Layout till now on this, we are not getting the this is the model files, and it is not there in the market. That is why layout we have not done. Nanoware GA8, not that much this one famous on if you will compare with FinFET. So yes, FinFET is doing good now. And after that, there are different things like the nanosheet FETs, nanoware FETs also are there. And TFETs are also there. So let's see after 2023 what will happen. But now I'll tell that this FinFET is is attracting more.
Okay, sir. Okay, dear participants, shall we close the session?
Yes, sir.
Thank you, Umakanta sir, for your valuable time today for us. Arpita ma'am.
Sir, am I audible, sir?
Yes, yes, you are audible. Sir.
Thank you, sir.
Thank you very much for inviting me. And yes, it was a nice talk, and after that discussion also. So thank you very much. Should I leave, sir, or anything else?
Thank you, sir. Thank you for the wonderful session. So thank you for
Thank you,
sharing
madam.
your valuable insights with us, and we wish to hope to have you again in the future, sir.
Thank you, madam. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Okay, dear participants, now we will move on to session 6 of our FDP. Our resource person from NIT Warangal, Dr. P. Sriharrao Garu, Professor of ECE, have already joined us. Before we hand over the session to Sriharrao Garu, Arpita ma'am, please
Sir.
introduce briefly Sriharrao sir to this meeting.
Okay, sir. Good evening, sir.
Sriharrao Garu, welcome, sir. Am I audible, sir?
Sriharrao, sir.
Good evening, sir.
Good evening, sir.
Good evening, madam.
It is my good evening, sir. It's my absolute honor to introduce the session 6 distinguished speaker, Dr. P. Sriharrao, sir, who is currently serving as Professor, Department of ECE at NIT Warangal. Dr. P. Sriharrao, sir, holds a PhD in Power Management IC Design from NIT Warangal and MTech in Communication Systems from IIT Roorkee. Over the last 30 years, he made significant contributions as an educator and researcher, with teaching for 4 years at Thapar University and the rest at NIT Warangal. He has taught a range of specialized subjects including analog and mixed signal IC design, RFIC design, CMOS VLSI, and digital communications, shaping generations of engineers and scholars. His research interests include power management ICs, smart SOC design for IoT, smart sensors, and search circuits. He has successfully guided 7 PhD scholars, over 30 postgraduate theses, and is currently supervising 13 PhD students. He has also taken on numerous leadership roles, including chairman of E&ICT Academy at NIT Warangal, head of the EC department, and faculty in charge of Center for Innovation and Incubation. His active involvement in committees, clubs, and IEEE events highlights his commitment to academic excellence and institutional development. His research spans a broad spectrum, including power management ICs, smart SOC design for IoT, and smart sensors, and he has led and contributed to 13 major R&D projects with a cumulative funding of over 20 crores, sponsored by prestigious agencies such as MIT, DOT, ISRO, DRDO, and MHRD Spark. He successfully fabricated and tested integrated circuits such as power management ICs for smart probes, adaptive LDOs for mobile applications, and smart temperature sensors and energy harvesting circuits for IoT. He has an impressive research record with 34 SCI Index journal publications, 44 international conference papers, and 3 international patents. He has also received notable recognitions, including the Best Research Paper Award at IFIP IoT in the year 2021, senior membership in IEEE, and AIR recognition under the Kapila program. He mentors 7. He's an active reviewer for top tier journals, including IEEE Transactions and Oxford University Press, and has contributed to curriculum development and quality assurance as a member of Board of Studies and government bodies over several universities and institutes. In addition to his academic and research credentials, he has played a pivotal role in fostering innovation and entrepreneurship on campus, establishing the MSD Lab, supporting over 20 student startups, and securing NBA accreditation for both UG and PG programs. He is also actively engaged in global academic exchange, including collaborative work at Arizona State University, and has hosted GIN programs with faculty from University of Illinois, Urbana Campaign, and University of South Florida. We are truly honored to have you, sir, for this session, who has a rare combination of vast technical expertise, leadership, and academic vision. I am truly honored to read your biodata also, sir. So I invite you for this session.
Thank you very much, Professor Arpita ma'am.
Thank you, sir.
I profusely thank even Professor Srinivas Rao garu for inviting me to deliver the talk. Hope my slides are visible.
Yes, sir. Your screen is visible.
Yeah, I'm going to slideshow mode. Is it visible?
Yes, sir. First slide is visible. Please change the slides. Yes, sir. They are changing.
Okay. So shall I start?
Yes, sir. Yes, sir. Please.
Yeah. Of course, without break, we are starting between the two sessions. Hope
Yes.
the participants they can just listen at their own pace. And of course, I am also a little bit slower now due to the prevailing other conditions which I already mentioned. So let's try to just start. The topic is intricacies of the mixed signal IC design. Hope I'm audible.
Yes, sir. Audible.
Yes. So what is a mixed signal integrated circuit is the question here. So what we are going to just deal for this period is we have divided into two parts. We'll try to see some of the intricacies of mixed signal IC. First of all, the significance and the intricacies, and then some one or two case studies will be demonstrated through the tool. So let's try to look at the mixed signal integrated circuit. Of course, as the name implies, it's a mixed in the sense what is mixed here? Analog circuits and the digital circuits. They are supposed to be fabricated on the same single semi-conductor die, right? So it's needless to mention that any gadget nowadays is a mixed signal substrate. It's a mixed signal IC or mixed signal system. The reason being, by the virtue of the advantages of digitization, we generally would like to process the signal in the digital domain, whereas due to the unavoidable compulsions, we need to continue some part of the signal chain in the analog domain itself, right? So what is the necessity of continuing the analog subblocks? Anyone would like to answer from the audience? So the mixed signal system basically consists of both analog and digital blocks. Then all of us are well aware of the advantages of digitization. So therefore, we would like to convert everything into digital systems, but it is not possible. So we are continuing with the both analog and digital subsystems in the overall system. So what is the necessity of continuation of this analog subsystems is the question.
Physical phenomena, natural phenomena are in analog in nature.
Excellent. So the physically available signals, they all, majority of them are analog in nature. Analog in this is continuous in time as well as amplitude, right? So
Yes, sir.
therefore, you need to, whenever you are extracting, for example, I'm speaking, therefore they say it's a mechanical signal, it's continuous in time. So if I try to just know, if I have to collect the signal, then I have to do it in its original analog domain, right? Because the nature itself is analog. Therefore, the extraction of the signal, or the collection of the signal, should be in the analog domain. And subsequently, before we process the signal in the digital domain, we need to condition the signal also. Because signal in its original form is very weak in nature, and it is to be processed in its original domain. If we try to digitize right away, the problem could be the signal will die down in the presence of quantization noise, right? So we need to make it sufficiently strong before it is fed to the corresponding data converters for digitization and subsequent processing in the digital domain. So this conditioning also includes, it could be filtering from the background or surrounding noise, and also amplification and other associated processing. So you want to do that. What are the challenges here? So the fundamental challenge for this in the IC design context is, as technology is being scaled down, digital subsystems do allow all the scaled down technologies to be used straight away. That is, the digital subsystems can exploit the advantages of scaling down the technology. They can adopt straight away, whereas analog subsystems will trail behind. What could be the reason? What could be the reason? What could be the reason? Let's try to make this session a little bit interactive so that it will not be monologue.
Dear participants, you can unmute your mic and respond to Srihadrav sir.
The various levels, sir, voltage levels.
Yeah. To be more precise, what happens is, whenever you scale down, the supply voltage also gets scaled, right? So when this technology is being scaled down, supply voltage also gets scaled. Why should we scale down the supply voltage? Because the other class, you are listening to some nanometer technology, particularly it is 3 nanometers or 7 nanometers or 14 nanometers, whatever. So the technology, as it is being scaled down, the supply voltage also is being scaled down. Why should the supply voltage be scaled down?
Device parameters are changing. That's why supply voltage is changing.
Strictly speaking, as the technology is being scaled down, number of transistors per unit area are going to grow exponentially. Therefore, what happens if we retain the same power supply, this higher power supply, then the electric field intensity will be enormous and the transistors will break down, right? So you have no alternate but to scale down the supply voltage. Well, you try to scale down the supply voltage, then as far as the digital subsystems are concerned, the scale down supply voltage is no issue, briefly, because the performance will not vary much. All that required is to identify a high level or a low level. So there's no big deal over there, but for slight degradation in the noise margin. But as far as the analog counterpart is concerned, you need to reproduce all the signal levels. So therefore, as the supply voltage scales down, the major problem is the noise almost remains the same or may increase due to the more number of the devices. So the signal to noise ratio is greatly degraded, right? Because signal to noise ratio is greatly degraded, it is really a challenge to design the circuits which are very sensitive to the noise, and the signal is very, very feeble. So this is one of the fundamental challenge. And other challenge is the threshold voltage doesn't get scaled down as the supply voltage is being scaled down, right? So what is its impact on the circuit performance as far as the analog circuits are concerned? Anyone? If the threshold voltage is not being scaled down at the same rate as the supply voltage, then what is its impact? I'll put the question the other way around. If you want to design an amplifier, in which region should you bias the MOSFET so that it can act as an amplifier? The options are A, linear region, B, saturation region, C, cutoff. Which one do you opt?
Linear.
Linear region.
Linear region. Any other answer anyone would like to add? So I think we need another platform to address these issues. But then let me try to answer quickly. Take it granted, because analysis, this is not right now we are not looking into those intricacies. So it is the saturation region that we bias the transistor for it to be used as an amplifier, not the linear. We want to use it as a switch, we will bias it in the linear region. We want to use it as an amplifier, then see, unlike the BZT, here we are now referring to MOSFET. So it should be biased in the saturation, right? Because in the saturation region, the current varies only in response to the signal that is applied at the gate. And current is constant against the drain to source voltage variations, which we exactly want. Whereas in the case of a linear region, the current varies both as a function of applied gate to source voltage as well as drain to source voltage, which we don't want. Okay. Therefore, we need to bias the transistor in the saturation region. Not only that, the transconductance GM falls with the supply voltage, or I should say, it's a VDS basically. So the
Srihar sir.
Yeah.
Are you changing your slides?
No, I have not changed so far.
Okay, sir. Okay, so just to confirm. Sorry, please go ahead.
No issue.
Okay.
So we have to look at the transconductance. Transconductance in the linear region and transconductance in the saturation region, if you have to compare. Transconductance in the linear region varies with the VDS, or output voltage, I should say. So as the VDS falls, then the transconductance GM also falls. Whereas that means as input voltage is increasing, for example, if you consider a single common source amplifier, then as input voltage increases, the current increases, and then IDRD increases, and VDD minus IDRD is going to fall, right? So in which case the GM also falls. It's a danger. So as GM falls, the gain also falls. Whereas in the case of saturation region, transconductance is not a function of the output voltage, right? So transconductance indeed remains constant. You can derive the transconductance. It is a mu Cox W by L into VGS minus V threshold. It is independent of VDS. Therefore, we prefer to bias the transistor in the saturation region if it has to function as an amplifier. Not only that, these two reasons put together, also we can conclude that the R0 is very large. Therefore, we can also once again emphasize that the transistor is to be biased in the saturation region if you want to use it as an amplifier. Right. Okay. Now, why did we discuss this point is what happens as the technology is being scaled down, the threshold voltage is not being scaled down at the same rate. So for a transistor to be passed in the we have all now agree that the transistor is to pass in the saturation region if you have to use it as an amplifier, right? If that is the case, then what is the condition to be fulfilled for keeping the transistor in the saturation? The condition is that VDS should be greater than or equal to VGS minus V threshold. So if VDS is to be greater than VGS minus V threshold, that is at the output node, you need to maintain a minimum value, DC value, VGS minus V threshold. If the supply voltage is being scaled down, as the threshold voltage is not being scaled down, then VGS minus V threshold is not coming down, right? Much. Okay, that's one point you have to keep in mind. And so, what is the maximum possible signal excursion? Maximum possible signal excursion is between 2 points. Lower point is, I said VGS minus V threshold. What is the upper point? What is the maximum possible value of the signal in an amplifier? Maximum possible value of the signal in an amplifier is
ACC.
great. VCC, or we say in this context VDD, right? So the signal changes between VDD and the maximum value is VDD and the minimum value is VGS minus V threshold. Between these two only, the dynamic range of the signal will be there. So now what happened? As the technology is scaled down, VDD is coming down, therefore maximum possible value of the signal is coming down, but threshold voltage is not going down at the same rate. Therefore, minimum possible value of the signal is not going low, right? So the net effect is the total available dynamic range of the signal at the output of the amplifier is terribly reduced, right? So this is another problem which is associated with the analog IC design, which is not there with respect to digital IC design, right? So now what is our challenge is we need to put this analog subsystem and digital subsystem both together on the same substrate, and we have to live with it. So just now we have identified that I cannot scale down the supply too much in the case of analog as compared to the digital. So therefore, the power supply requirements are different for analog and digital subsystems. Ground requirements are different. and nature of operation is different. So different working conditions, but then you have to live together. That's the challenge of mixed signal IC. Okay. So typically mixed signal chips perform some whole function or some sub-function in a larger assembly, right? Such as you can take radio subsystem of the cell phone or read data path and laser slit control logic of the, of course, DVD players are not there nowadays. So overall, I can say that there are multiple, indeed, every system is now a mixed signal system. It has got, because the signal chain, both at the beginning, at the end, there are analog subsystems, and in between, digital subsystem is there. Therefore, altogether, it is, every system is a mixed signal system, and but both of the analog and digital have got their requirements to be different. And these are the examples I mentioned already. So best example is a data converter, and then another one is a, right, data converter has got analog input and digital output, right, and a comparator and so on. They are mixed signal circuits, of course. Okay, and so as these points are already mentioned, that because the use of both analog and digital signal processing, mixed signal ICs usually are designed with a specific purpose, and the CAD tools also have to raise the bar, and continuously there has been exploration on of improving the performance of the mixed signal circuits, particularly in the usage of the CAD tools. So automated testing of the finished chips can also be challenging, and for the mixed signal circuits, the testing, if you want to make it complete automation, it's again a challenging. So there are various role players who are supplying the mixed signal circuits or ICs. So the global mixed signal IC market was valued at $122.9 billion in 2023, right? And it kept on increasing exponentially, and propelled by the increasing demand for the consumer electronics, such as smartphones, tablets, and wearable devices. The need for the power efficient and high performance solutions in the consumer electronics is pushing the manufacturers to adopt the mixed signal ICs, and thereby driving the market expansion. So the growth drivers are the rising demand for the consumer electronics, automotive electronics, right? For example, if you look at nowadays car, majority of the role is being played by electronics rather than the mechanical items, right? And electric vehicles. So growth of the IoT and the connected devices, and advancements in the 5G and beyond networks, increased demand in the industrial automation and so on. So the challenges I mentioned a couple, there are many more. Complex design and verification challenges, high development costs they're going to pose market hurdles, right? And so the mixed signal IC industry is witnessing significant trends which are driven by the advancements in the AI and ML. As I mentioned, the digital counterpart can quickly adapt to the changes, and they can exploit the advantages of the AI and ML, and therefore automation can be done. But in the case of the analog counterpart for mixed signal, the problem is, in the case of custom IC, you cannot just completely have a foolproof model, right? So, for example, what is required for AI and ML? You need to have a lot of database, right? But here, depending upon the specifications and all, the system design keeps on changing. It is not exactly the same, so you can't just predict the design because the environment keeps on changing, and then the design intricacies keep on changing, and it is a you're dealing with analog signal, and therefore custom IC design you cannot automate the way you can automate for the corresponding digital counterpart. Therefore, these technologies are increasingly being integrated into the design and verification process and allowing for faster and more accurate simulations of complex and mixed signal circuits. Yet, the ANML, we are trying to just bring in to the extent possible in such a way that we would like to reduce the turnaround time, right? So we will try to, though it is 100% replacement is not being done. That means it just like the chat GPT just now, hey, please give me a solution for so-and-so specifications of a mixed signal domain. Then probably we don't have any such solution by the AI ML as I know, right? But still, some rough model probably is being evolved, and that is trying to reduce the turnaround time or iterations between the simulations. So AI accelerated verification tools, such as those, of course, Siemens is trying to explore, and by automating many aspects of the verification process. So it reduces the time to market while ensuring the reliability and performance of increasingly sophisticated ICs. And a growing adoption of the mixed signal ICs in the emerging technologies such as 5G, autonomous vehicles, and Internet of Things. And they require ICs that can handle high-speed data processing, complex signal conversions, signal conversions from A to D and so on, and low power consumption in the compact format and so on. So rather the smart devices and wearables is pushing the need for the ultra low power mixed signal ICs that can extend battery life while maintaining the high performance. This is another important area, the power management IC design. So your phone, when you're using, you love that it should work for a long time without going for recharge. So in spite of the high-end functionality in place. So that means though the different subsystems in your mobile have got different power requirements, there's only single power source, which is battery. So from the battery, you need to derive the requisite power only and deliver it to the individual subsystems. For example, there can be analog subsystem which requires 1.2 volt. There can be a digital subsystem which requires only 0.9, 0.8 volts or whatever. So there can be another analog subsystem which requires 1.8 volts. So without wasting the power, we should be able to cater to the individual requirements of the different subsystems. And also we should see that if the load suddenly varies, that is suddenly turn on the flashlight, or suddenly turned on the camera. So then what happens? I require more power. And irrespective of these load conditions, the supply voltage should remain constant. Okay. So, or not only that, even as the battery keeps on getting discharged, performance should not change. That means the power supply is going to play a vital role in the overall performance, right? So therefore, this is a power management IC is another important area where the mixed signal domain has been exploring, and it's evergreen research area. And mixed signal IC market, of course, as I mentioned, 2022 is $115.5 billion, and it kept on increasing exponentially the market. And these are the various sectors which are taking lion's share in the IC design industry. So what are the challenges? CMOS technology is usually the optimal, and digital, as far as digital is concerned. And of course, even for the analog also, CMOS is pretty handy, right? And the advent of the technologies like high performance CMOS, by CMOS, SOI and silicon germanium, they have removed many of the compromises that previously had to be made. And just now you had one class, one session about other than CMOS, what are the technologies that being explored, nanowires, right? All these nanosheets. So these still this exploration is being take place. If I'm not wrong, as and today, there is no practical replacement for CMOS technology. So all others are still in the exploration state only. Therefore, if one wants to work in the industry as and now as it is, then one should get the expertise in designing the circuits using CMOS. Then you are readily absorbed in the industry. And so the testing functional operation of the mixed signal IC demands is really complex and also expensive. System design methodologies comparable to the digital design methods are far more primitive in the analog and mixed signal arena. And analog circuit design cannot generally be automated to the nearly extent that the digital circuit design can, as I already mentioned. So combining the two technologies multiplies the problem or the complication. So fast changing digital signals send noise to the sensitive analog inputs, and you know that as far as the digital circuits are concerned, their operation is basically switching between 1 and 0 at a very fast rate. So this digital subsystem, which is switching very fast, is located on the same substrate as that of the analog counterpart. Therefore, what will happen? It gets coupled to the sensitive analog input, and analog fellow, poor fellow, he cannot distinguish between this switching noise, which is being switched between VDD and ground, whereas the analog signal is very feeble in nature, and therefore what is going to happen is the poor analog system cannot distinguish, and it will succumb to the switching noise, and then the output is chaos. So there are various techniques which are being employed to minimize the noise coupling, fully differential amplifiers, P plus guard rings, differential topology, and so on and so forth. So this is the example of the MSD already mentioned. And so with the reduction in the feature size, the mentioned RF circuit issues becoming dominant in both digital and analog circuits. So let's look at noise issues. So this coupling noise, component noise, power supply and ground noise, and coming to circuit parameters, impedance mismatches, gain, and analyzing methodology and tools, and so on. So as I mentioned, the requirements for the digital subsystem and the analog counterpart are different. As far as the digital is concerned, you can see that high speed, high levels of integration, low cost, and low power are the issues. Whereas in the case of analog requirements, high speed and low input capacitance, high accuracy or low offsets, and low cost, and analog component availability, and low power, and so on. So the corresponding process which is more suitable depending upon the requirement, the comparison table is also shown to you. And so of course the flow is similar, conventional, we all are aware. And so the specification for the mixed signal is really complex. Too many decision parameters are there, and the design is concerned, diverse fields of specialization are required here. And verification, again, analysis of multiple domains. So evaluation is a statistical analysis. Fabrication, of course, is a system on chip fabrication. Please remember that whoever wants to pursue their career in the domain of mixed signal, there are multiple facets here. It could be digital IC design, it could be analog IC design put together, and then tool design, and what else? So the verification, of course, is a somewhat low resistance path to reach the industry. So, but then in the long run verification, I don't know how far the engineer sustains, because the AI is really doing a lot of damage to the job sector, particularly where as far the automation is concerned. So of course, new jobs are to be explored, but then definitely if one would like to make only verification as career, I'm only mentioning from the viewpoint of choosing the career path. If one wants to go for verification as only the career path, what happens is in the long run, then probably once AI completely automates the verification process, then it will be difficult for those engineers who only rely on the verification. So my urge is only that one should have a complete knowledge about the design and of course verification, so that whenever whichever is required by the industry, one can adapt himself or herself. So the specifications should be very unambiguous, and feasibility with the current technology should be there, and the functional parameters and the throughput is also very important. Analog parameters like bandwidth, gain, and threshold are also important, and design parameters, area, power. So there should be trade-off amongst all these specifications like speed, power, cost, and functionality. So while laying out the components for the mixed signal PCB, certain considerations are critical to achieve the optimum performance. Mixed signal is practically pretty tricky to design. The reason being the analog devices possess different characteristics as compared to the digital components. So different power rating, current, voltage callouts, and heat dissipation requirements. And therefore, as a consequence of this, it is important for the design engineers to recognize certain problematic areas and then implement them correctly in the mixed signal domain. So as far as the noise is concerned, mixed signal IC design frequently leads to non-functional devices because of the noise problems. Large amount of the digital noise is combined with the sensitive analog circuitry is going to result in the interference, right? So IC noise coupling is not properly modeled and simulated. Therefore, this leads to devices that simulate correctly but have functional or performance problems on the silicon due to the noise. Please remember that you design something you simulate and you think that it's working, but then when it's fabricated, probably it fails. So therefore, it's very, very important to anticipate such problems to the extent possible during simulation and then try to offer some solutions. So for the next few minutes, we'll try to look at a few such problems and then offer some solutions. So as I mentioned, digital transition switching is the primary cause of the noise in the mixed signal devices, right? So you can see very clearly is a simple example of inverter to choose. So during transition between 1 and 0 or 0 and 1, then supply is connected to the ground, and therefore, therefore what happens is the power dissipation takes place, and also as it is being switched here, so switching noise comes out. So here we call it as a noise because for the analog counterpart it is noise. For the digital it is the voice. So it is between VDD and ground you are changing at a fast rate. But then what happens is when this gets coupled to the through substrate to the analog counterpart, it is going to be appear as a noise for the analog counterpart. So as the digital inputs transition between the low and high states, the gate briefly provides a resistive short circuit between the power and ground, and digital rise or fall transitions also produce wide bandwidth noise, which can couple to the adjacent circuits. So nevertheless, most ICs have a large number of the gates which are switching under clock control. So therefore, put together, this leads to significant noise. So now, one such example is the ground bounce. What is the ground bounce? If you look at the transients have much of the spectral content in the higher harmonics of the clock. For 100 megahertz clock, noise above 1 gigahertz is supposed to be common. So consequently, the spectral content of the transition switching becomes a RF noise problem, right? At the RF, all the parasitic capacitors, they start to become transmission path. You know that MOSFET itself is bigger of the capacitances. So these parasitic capacitors, CGS, CGD, CGB, right, and they become short circuit. So in addition, interconnect inductance metal connections, bond wires, and package lead frame, they have a significant effect at these frequencies. So therefore, we'll try to just look at one such ground bounce problem. So when the base of the NPN transistor is turned on, for example, enough current flows to the emitter, right, to the emitter collector circuit. And what happens? The silicon in that area is in the immediate vicinity of the emitter ground connection is pulled partially high, sometimes by several volts, right? So therefore, what it raises the local ground to a value significantly above the ground. So relative to this local ground, the base voltage can go negative, right? So as base voltage can go negative, what happens? It shuts off the transistor, right? So because VBE becomes now as the emitter is now going a little bit momentarily high, and therefore relatively VBE becomes low, right, or negative. Then what happens? It turns off the transistor. So as the excess local charge dissipates, the transistor turns back on, right? So possibly causing a repeat of this phenomenon, sometimes up to half a dozen bounces during the switching period. So that means what is happening there is the ground potential is being just rising, and by the virtue of which the transistor is being turned off and again turned on and again turned off. So as the switching process goes on, right? So therefore, this is the ground bounce, and as I mentioned, there can be this can be more easily see here. This can even supply bounce also is possible, and this is ground bounce. So there are this is the node is connected supply. For example, supply node is connected to the IC pin through the bond wire, right? So therefore, there will be inductance here, and inductance, the reactance. We know that inductance doesn't respond quickly to the sudden changes. Therefore, the current through that, you can see that it's LDI by dt, the change. So as there's a sudden change, therefore the voltage that it develops is LDI by dt. So therefore, by the virtue of which the potential changes. So as the potential changes here, then as I said, the total dynamics of the circuit is going to change, right? So therefore, there can be ground bounce, or otherwise there can be, for example, so this node potential may rise as in this example I told you, if the inductance value is 5 nanohenries and the current change is 10 milliamperes change is there in the current, and over a period of a nanosecond, so it can drop as high as 50 millivolts. If the current is of 100 milliamperes, then 500 millivolts drop also is possible. So such a large change, the drop across this, that is at this potential. So what is happening is the potential is rising and momentarily, and then again it goes off. So by the virtue of which the dynamics of the circuit is going to change, and so there is a possibility that the the transistor is being turned off and on inadvertently. So we have to just address these issues, right? So digital signal integrity becomes an issue when the magnitude of the problem exceeds about 1/4 of the power supply voltage. So mixed signal designers have more stringent noise and power stability requirements than do the designer of a digital domain, so frequently under 1 millivolt. So interference noise should not be confused with the inherent noise or distortion. So in addition, thermal and flicker noise sources are usually much smaller, though they are smaller, but then they also play a vital role. So they are smaller in the magnitude than the interference noise. Please remember, there are ways and means through which you can try to minimize the flicker noise. For example, if you want to reduce the flicker noise, you have to use white transistors. Right. So I want to reduce thermal noise. There are circuit strategies like use what call in the op-amp design. Which one you have to use as a P-type input as the input stage, or the counterpart, n-type input transistors are used in the first stage of the first stage. I means the differential amplifier stage, right? And therefore, if you use a p-type input in the differential amplifier stage, and they'll use a n-type common source n-type input you'll use for the common source following common source amplifier, and vice versa, right? So therefore, there is a trade-off in reducing thermal noise in choosing appropriate choice of such p-type input or the n-type input. And similarly, for the flicker noise also, there are solutions mentioned. So, but the interference noise is much higher in magnitude than these two, because they are occurring, though their magnitude is a lot, but then they're occurring momentarily, right? Because of their momentarily appearance, their impact is seen in a larger context. So, what are the approaches to reduce this noise is the question here. So it's very important, though people, one might think that he is speaking about all this. So, a performance, when it comes to performance, ultimately you design, and at the end of the day, after the fabrication doesn't work, then you really wonder why what's happened. So if you don't take such very fine measures during the design, then obviously the IC fails. So we'll do some, we'll keep some nomenclature here. Transmitters, we call them as talkers. They are the noise sources, and receivers are the listeners. So noise is basically listeners. This is a noise susceptible circuit, right? So what are the approaches here? Yeah, can I try to attempt to reduce this noise post-fabrication or before? So post-fabrication is not desirable because I cannot have a complete control over that. Therefore, consider the noise issue as a part of the design process and that is anticipated beforehand, and include the noise immunity in the original design itself. So that's the best solution that you have to adopt. Now, so what are the ground bounds we already discussed in detail. So ground bounds counter methods, let's take a look at. I've listed some of them, right? And a couple of them we'll try to look at. So place a bypass capacitor close to the affected component. So physically, the bypass capacitor acts like a battery that compensates a change in the die ground potential as measured with respect to the power rail. So the bypass capacitor also accepts some current from the discharging load capacitance when the driver switches. Also, place the bypass capacitor as close to the VCC pin of the component as possible to minimize the total inductance of the ground trace. So what are the factors that increase noise problems? Increasing the switching events caused by the larger gate current or higher drive strength gates. And IO cells are especially problematic due to the large currents necessary to drive the external loads. Right. So we when you want to drive the external loads, of course, you need to drive. For example, there's a is it the flash is there? So the flash that you want to just suddenly turn it on, then obviously what you have to do is this fellow has the circuit has to drive large current. So increasing the clock frequency can increase the noise too, because the inductance of the interconnects and coupling capacitance is more problematic at higher frequencies. And proximity of the noise transmitters to the receivers. So after all, everything is embedded into the same chip here, and however far you want to push, but it cannot be much, right? So close proximity interconnects will have coupling capacitance, and currents cause magnetic fields and consequent transformer coupling effects as well. Also, the adjacent bond wires can couple the signals. So every circuit element is coupled to the substrate. Therefore, what happens? Everyone is coupled to sub. For example, you are living in an apartment, then on a particular floor, right? If you try to look at, you are in the ground floor, and the first floor fellow, not only that all the people who are there in the different flats, of course. So all of them are connected to the same floor, and therefore, if whatever the noise they make, everything is visible or is audible to the ground floor floors, right? So every circuit element is coupled to the substrate, and noise generators and potential noise receivers can be coupled through the substrate as well. Okay. So this is how I said this is called aggressor. This is aggressor is basically one who creates noise, and this is a poor fellow victim here. So, but this fellow is going to substrate. This fellow is also going to substrate, and therefore through substrate coupling like this, so this fellow is a victim of the noise. So noise generation and reception is a distributed problem. It's not a lumped problem, right? Most ICs, they have multiple sources and receivers. Transmission switching is not just digital, and analog circuits such as comparator outputs and oscillators, they can be noise generators within the analog circuits. So though we've been telling that, oh, digital fellow is creating noise all the time, analog subsystem keeps on cribbing. But my dear friend, analog fellow, you also have some troublemakers, right? Comparator and oscillator. So they also can create noise. So due to the distributed nature of the problem, most effective solution is often a distributed methodology. Okay. So this is what is the scenario I already mentioned. So what are the solutions? We have just now seen some of the problems. So provide low noise, low impedance connection for the power, ground, and substrate. So also make any listener which are less sensitive, right, to the noise. To the extent possible, don't make them more sensitive to the noise, because, for example, it's just not practical. In the class, you have your mobile adjacent to you. All the time you are now prone to the noise from the mobile, because now mobile is not the source of the voice. So therefore, you try to make it less sensitive. Then what you do, you just keep it in mute and keep it away, right? So similarly here also, so to the extent possible, try to see that listeners are less sensitive to the noise, and suppress or silence the talkers, and separate the talker or the listener either by the proximity separation, time separation, or frequency separation. So noise sensitivity reduction by the fully differential, of course, this is a conventional one which you can approach. What happens is, whatever the noise that you make it is common mode, and whatever the voice or the signal make it a differential. Obviously, differential signaling rejects the common mode noise, and common mode rejection of 30 dB or more is common. Okay. So you can just now see this, whatever I mentioned. This is the noise here, and signal is this differential. Noise is common, and therefore, since it's common, it appears in a similar fashion in both the differential signals, and therefore that anyhow you're going to reject the common mode noise. Therefore, that is removed, and output is cleaned from the common mode noise. Therefore, the bottom line is make the, to the extent possible, try to go for differential signaling. Next solution is usage of the low pass filter. Analog signals can tolerate some high frequency noise if the circuits operate with a low bandwidth. My dear friends, in the entire system, wherever there are subsystems who operate only with the low bandwidth signals, unnecessarily don't go for larger bandwidth. For example, there's an audio amplifier. You design an amplifier for only audio frequencies. But then, because my technology is permitting, I am designing it for 100 megahertz. It can, it have a beautiful bandwidth. The specification says only 50 kilohertz. But then I have designed it for 100 megahertz. What is there in it? It amplifies 50 kilohertz beautifully, So excessively you have designed what is it? There's nothing wrong if you think there's a suicidal attempt. What is to be done is unnecessarily don't go for overkill of the spec here, because it invites unnecessary problems. The switching noise is much beyond this bandwidth. Then you are inviting, oh, please come inside, right? So therefore, you try to exploit the advantage of the circuital requirement, that if you require low bandwidth, don't go for unnecessarily designing with more larger bandwidth. Then what happens is the frequency which is in the higher range of the frequencies, so the switching noise which is at higher frequency range can easily be filtered out without your explicit intervention. Okay, so using minimum bandwidth circuits helps to avoid the amplification and retransmission of the switching noise. High frequency noise can pass through any circuit without gain due to the direct coupling through the circuit's parasitic elements. So that you can't help. The passive low pass filters will help to reduce this, and this low pass filter cutoff frequency should be less than the system's clock's fundamental frequency. Okay, so but this is the story of the circuits which are having the requirements of the low bandwidth. But how about the circuits which are whose bandwidth is high? So high bandwidth circuits are more susceptible to noise, especially if they pass the frequencies that include system clocks and their harmonics. So then what to do is try to keep the IC's sensitive signals internal. So unnecessarily don't bring any sort of connection out. You say that while designing the IC, yeah, I can just do this connection outside, and therefore there I'll try to. No, to the extent possible, now keep the IC sensitive signals, particularly sensitive signals internal only. So don't bring them out. So going outside the chip opens up more opportunities for the noise degeneration of the signals. Therefore, try to keep all the sensitive signals within the chip itself. So it's not a big or a new thing as far as the human life is concerned. For example, in the family, the wife and husband relation, there are these sensitive signals. These are, don't expose it to the outside world unnecessarily, because so many things they come inside and then it spoils. So therefore, analog signals will be less sensitive, less noise sensitive when kept as large as possible. Also, you try to keep the analog signal to the extent possible as large as possible, so the signal to noise ratio improves. Right. So small amplitude signals are often within the an on analog or preamplifier circuit. So high gain circuits such as the comparators should be bandwidth limited, as they are more noise sensitive. Therefore, what you have to do, suggestion here is use hysteresis topology. Okay, so and now the power, ground, and substrate stability is concerned. Low impedance connections for the power and ground are usually, they provide quieter power supplies, and keeping analog and digital powers and grounds separated, they should provide to improve the power and ground noise, right? So in addition, the transition switching noise is undesirable in analog power. So SPICE simulations often they use ideal voltage source to represent the system power. Okay, therefore that actually it leads will be misled by it. The simulations show quiet power even when the high surge currents are present. But in the actual silicon, what happens? These circuits will have some impedance and high noise problems. Therefore, what is to be done? While simulation, it will take this also into account. Okay. So internal power filters are especially valuable for high frequency noise. Analog circuit layouts can have empty locations which are filled with the power supply filter capacitors, and stacking the power and ground interconnects providers, it is going to provide metal plate capacitors. It provides metal plate capacitors, and filters can be placed under the interconnect areas or beneath the power rails. Okay, so therefore try to make use of the filters to the extent possible that filters out the noise, right? So the metal interconnect areas are often sizable, and layers underneath them can be used for the power filtering. So this method can provide sizable internal filtered capacitors without increasing the IC size. So design rules for the substrate contacts are specified to cover latch-up protection issues, but they are not defined to deal with the noise concern. This is important to just not keep in mind. So as far as the latch-up is concerned, it is taken care by the design rule itself. You need not do any special attempt here. But as far as the noise is concerned, there is no answer from the the design rules. So therefore, as a designer, you have to take care of it. As a result, the required amount of the substrate contacts are usually insufficient to deal with the substrate noise. So for P-type substrate or P-substrate envelope CMOS process, if you try to see, a substrate contact or tie-down, it consists of a P plus area in the substrate that is connected to the ground. It will be seen here. See here. So in general, the first solution, which is part A that's shown here, so is conventional. What it does, it avoids the latch-up problem, all right, but then that is not sufficient to take care of the noise. Therefore, what you do is the solution which is shown here in the part B, that is adopted to reduce the noise here. How? What it is going to do? So the substrate noise, if you want to just reduce, what you're supposed to do is, so the substrate contact or the tie down, it's a P plus area in the substrate that is connected to the ground, right? So you can see this is a P plus area, whereas here is only P type substrate, whereas though it is not required, I'm using a P plus intentionally so that this P plus is connected to the ground here, and much lower resistance is it's going to offer than substrate. It provides a good ground connection. So substrate noise should decrease with the employment of the grounded substrate contacts, and grounded contacts should be distributed extensively in the circuit layout, closely surrounded by all noise generators and surround all the noise receivers as well. So grounded contacts, the proximity to the noise generators is very much valuable now to absorb the carriers before they are allowed to go deep into the substrate. Okay. So similarly, here you are going to use N plus tabs here. So they are the same scenario is shown in a much clarity. So you can see here that this is N plus, right? And now next one is the guard rings. So I think here you can see this fellow is a P plus fellow is connected to the ground here, whereas N plus is connected to the supply or vertical VDD. Okay. So now coming to the guard rings. So guard rings are used to localize the noise effects and coupling to the substrate. So guard ring can be implemented to both suppress the talker as well as isolate the listener. I mentioned that if to avoid the to reduce the noise, you need to suppress the talker and isolate the listener as well. Okay. So if there is a fellow who is making noise in the class, then you try to control him. At the same time, try to see that the attention of the listener is not distracted by the noise generator. So therefore, we adopt some guard rings, right? So guard rings consist of connections to both power and ground. And for the P-type substrate, annual CMOS, the grounded guard ring uses a low resistance P plus area to connect to the ground. You can see that. Okay. And so on contrary, in this case, we are using N plus region is connected to the VDD. Okay. So therefore, this is how we try to just safeguard the sensitive circuitry from the noise. So this is the big picture is here. So P plus God ring is connected to AVSS, whereas now the N plus God ring is connected to the AVDT. Okay, and there are many more solutions, of course. And so isolation, of course, the digital and analog signals should be kept away from each other. And so digital outputs from the analog cells should be separated from the analog inputs as well. And before we close and move to the laboratory demonstration, I just would like to mention that ADCs and DACs and comparators and similar mixed signal devices and analog and digital signals should be routed to the opposite ends of the device. And please see that when you want to design a mixed signal circuit, it's a bit complex here, and just the circuit design is not sufficient. You have to take many measures at the layout level to counter the contrast requirements and contrast situations of the analog and digital counterparts. There are many more intricacies and many more solutions, but whatever we have just discussed, at least one or two will be demonstrated in the laboratory. Okay, now over to lab.
Hello. Hello, sir. Hello. Hello, sir. Hello. Sir.
Hello. Hello, ma'am. Is it audible? Hello.
Sir, it is audible, sir.
Uh, is my screen visible, sir?
Not yet, sir.
One second.
Not visible. Not visible, sir.
Sir, now is it audible, sir? Sir, can you see my screen, sir?
Now your screen is being shared, sir.
Sir, good evening, sir. Sir, now we are going to see the sir, is my screen visible, sir? The cadence tool which we invoked.
Yes, yes.
No, I'm not asking about the terminal, sir. Have you seen? Only the terminal is coming, sir.
Yes, sir.
I want to share my entire screen. Sir, now you can see the CAW window, sir, cadence.
Yes, yes, sir.
Oh, sorry, sir. Now we are going to see what is the difference, how we are going to use the gatherings, and how we are going to implement the gatherings in the block levels. Hello. So we are using the technology of EMC 180 nanometers technology, CMOS technology. Here we are having it's 180 CMOS technology. Here we are using IC 6.18 version, and we are showing an example of we are taking one simple differential amplifier circuit, and we are showing how the gathering is going to work here. And we can see how the signals are going to interact with each other, and we can see how the aggressive is going to affect on the victim, and victim net are going to aggressive net. What is going to happen here, we are going to see that. And for that examples, we are taking a small differential amplifier circuit. Here the schematic. I think everyone knows how to invoke the designing everything. So now we are going to launch the layout. For that, we are going for launch layout Excel, create new. So here library name, already we have defined that gathering, and the cell name is a differential amplifier, view type, layout, and type. Based on our usage, we can change our mode. So I'm choosing now layout. Okay. After choosing, we are getting a window, which we are getting a layout window. This is the layout Excel. Before going to the layout, I need to say some basics. The black screen which we are seeing on the display, it's a P substrate. Because this is the CMOS technology. So CMOS technology is built on the substrate. So we are changing this one as the P substrate. The entire screen which we are seeing is a P substrate. So after launching that, we need to change these parameters. We need to change the display options. Like we need to change the snapping scale. It is predefined by the PDK foundry. Apply. Okay. Now I'm going to call the instance from the schematic. Already we have designed a small differential amplifier. So I'm taking the schematic. Before going to the schematic, we need to identify what are the circuits, what are the transistors we are having. Here we can see that these are the differential circuits, two different voltages which are coming into the circuit, and this is the current mirror. This is the tail current, and these two are the current mirrors. So here what we need to is, this is the main current source. You can see here, it highlighted. this current source. What is the current which is entering? This IDC is the pin. Initially, we are used to add a current source here. Here we need to add a current source. So instead of, we can't do layout for the current devices. So what we are doing is we are placing an pin. So this pin is used for current source. So what is the current that entering into this M2 transistor? It is going to replicate the same current into M3 transistor. So here M2 is the main transistor, because this is the current which is replicating from M2 to M3. It is a so M2 here, M2 and M3. So the same current is mirroring here. So this is called current mirror, this block. So if any changes happens in this circuit, I mean in this transistor, this current, I mean small changes in this transistor is going to reflect into the next transistor like M3. If it changes the M3, the operation of these two transistors is going to change, and they may changes to region, or it may come to cutoff also. So to overcome that problem, we need to protect this transistor, which you are seeing like M2 transistor, because this is the main transistor in this block. So what we need to do is we need to guarding this. We need to provide a one shell type. So for that, we need to invoke the transistors everything to here. Here connectivity, generate all from source. Here you get a pop-up window which is showing that generate IO pins, PR boundaries, everything. But now I am taking only the instance, so I am removing the IO pins and PR boundaries. Okay, you'll get the transistors. After that, we need to make them shift F. So you can see this. Totally, we have having instance which are in the same as schematic. 2, 4, 6. I am considering now in the schematic. I said no. This is the main transistor which we are going to consider. This is the M2 transistor. So I need to consider this. I'm shifting this one to upside. On the tail current, tail transistor is M3. I'm selecting these two and taking up. This is the M2 transistor. You can see here. Here in the instance, you can see M2 N18 mm. This is the transistor. The schematic. You can see here. This is the M2. So I'm taking this one as the transistor. The WL ratios are defaultly based on our usage. We have designed that. So here you can see the transistor which is having a huge gate length. So what we are having is the resistance, the voltage drop will be more here. So what we need to do is we need to divide this transistor. We need to fold this transistor, or we need to make this one into fingers mode. So for this one, I'm changing these properties. There are multi ways to doing this fingering offset, but I used to change in folding option. So it is default with this 20 micro. So I'm taking this one into 4. While we are doing this means the area will be constrained. The area will be constrained, and the voltage which is equally, it will be distributed equally to every transistor. Now I can share this OD. Actually, this transistor is having source and drain. One source and drain. One is connected to IDC and one other is connected to ground, and second is connected to duplicate current. So I am trying to share this OD. So, yes. Now the transistors OD is shared. Now we can see that source, drain, source, drain, source, drain. Everything is connected. Now we need to connect to gate connection. The poly. Here we can see the The blue color which you are seeing is the gate connection. It is the poly. Here initially we have taken L is 1 micro and width is 20 micro. So the length L is 1 micro and length have taken 5 into 4. Initially I have taken 5 and 4 transistors, 5 was 20. So equally sharing. So there will be no effect in the OD sharing. Now I have said that this transistor we need to protect this one. Protection means what we need to is sometimes not only from nets, some like while fabrication we are going to see some effects like layout dependent effects like WP effect, well proximity effect, LDO effect, and stress effects also we are going to see. Like what we are going to see, if any transistor, like sometimes some transistor are going to be sit like behind like this. I'm taking one replicate like this. So here in between this, some STA layer will come, shallow trench isolation. So due to that also we are going to see the effect on this OD layer. OD layer is the active layer of the transistor, diffusion layer. You can see the red box. This is the active layer. This represents the transistor behavior, the transistor OD, diffusion layer. So what we need to is, this is the main transistor. Here, what we need to is here, while inserting the formation of the source and drain, we are going for ion implantation. While doing ion implantation, what will happen? They won't do directly in a straight way. They won't do in this way. They use it to do at an angle, certain angle. So while doing ion implantation, there will be like STA effect. I already said that there will be here. Here, you can see STA layer. While doing fabrication, we can see STA layer. So while fabricating this ion implantation, they use it to replicate back into this OD layer, and the OD may be diffuser or it may go for under etching or over etching. To reduce that effects, what we need to is we need to add one dummy on both corners. We need to take one dummy on the left side, and then we need to add one more dummy on the right side. So what we need to do is there we can do like we can select this transistor and we can add one dummy. Like here we can see the create dummy ground. So what I need to do is I'm selecting a ground net. So why I selected the ground means whatever the like here we can see like sometimes in CMP, chemical mechanical polishing, we are going to see some that gate oxide is going to get some charge particles. So due to the charge particles, the transistor will be, instead of being in the cutoff region, it will be in like subthreshold condition, like weak inertia will be without applying any gate voltages. The transistor will be in like some voltage will be, some ions will be implanted in this one. So to reduce that one, we are taking the dummy as ground, because any implant, like while doing CMP process, chemical mechanical polishing, these ions will be inducted into this and everything will go to the ground. So the transistor will be in ideal position. So I'm taking two grounds. And I'm adding this back to here. Now you can see that this transistor, this is the active transistor. I mean, this is the main transistor, and I have added two dummy transistors on both sides, because if any implant, any effects are going to affect, means they are going to affect only on these two dummy transistors. Like if you are seeing the WP effect, well proximity effect, if this effects is going to be affect only on the dummy transistors. If you are going for high, if you are doing for mixed signals like high frequency signals, at the times what we mean to, the doping concentration will be has to be more. For that we can't expect that it's single dummy can't handle this entire thing. So for that at that conditions we are going for the guard rings. So not only for this, again we need to select this entire thing and we go for connectivity, or we have select everything and create. Here we can see multiple adding of garderings, we can, based on our research, we are going to see. Here I am going to use for protection layer. So we are going for multiple path, or we can go for shortcut key also. Select everything and Shift G. Here you can see two type of garderings, N-tap gartering and P-tap gartering. Already Srihar also said that about N-tap and P-tap. So what will basically the transistor is P-type. Basically the transistor is N-type. So I use it to take differently P-type, because these garderings, this body effectively, this body CMOS. The fabrication is built inside the CMOS technology. The substrate itself is a P substrate. To isolate between the P substrate and this transistor, I use it to go for annual gartering. That annual gartering is used only to protect that one, but is not getting any supply. So I need to select everything and I go for Shift G. Shift G is the shortcut key for creating a gartering. You can see based on the technology, we are using UMC 180 nanometers technology. Here we are having two type of garterings, N-type gartering and P-type gartering. Based on the PDK, they may be increased. I mean, we are using CMOS. If you go for BCD technology, they will come ISO rings and linear rings. Different rings will be seated here. Based on our usage, we are going to see that. So we are using here. We use it to select N-type. We need to seek rectangle. Apply. Hide. Now you can see that. Actually, this is the active transistor, and we have added two dummy transistors and one gartering. What now? What happening? If any ion implantation, like if we are doing ion implantation to form the source and drain, they use it to make it an angle of 7 degrees or 9 degrees. So at that angle, what happening? This OD, the ground transistors, and the if any penetrates without the ground and transfers into the VDD range, and these are all the VDDs. I mean, which are adding the garderings. So these are all garderings will be add to separate like VDD. It's like AVDD grounds will be there, and separate grounds and separate VDDs. They are specially designed for only for garderings. What have any charge particles which are invoked into that grounds, they will use it to nullify the grounds, that charge particles. And now we need to connect the transistors. After doing that, initially in the schematic, we have only in the schematic we did not find any dummy transistors. We find only the original transistor which are used in the designing. Now we need to replicate the dummies which are added in the layout, and we need to replicate that one into the schematic, because without doing that the LVS won't clear. So what we need to is first we need to connect this connection. Now I'm taking the metal too, and actually I use it to maintain. We use it to maintain that metal orientation, because all the metal one use it to in horizontal means we go for metal 2 in vertical direction to reduce the coupling capacitors. If you follow without following the metal orientation means what we need is that one more thing. What we are seeing in the layout is it is the top view. So what happened? Metal one used to fabricate, and after that again SiO2 layer on top of that we are going to see M2 layer. If M1 and M2 are placed in horizontally, what we are doing these two, like M1, M2 are formed in horizontal means, then we are going to see some coupling capacitors, because they are placed in horizontal. Like we can see like two railway tracks are traveling in same direction. If you think railway tracks, one is metal 1 and M2 is metal 2 means, then what happening? Coupling capacitors used to form throughout the distance of the metal. So to reduce that one, we are taking one as the cross and another one has another cross section. I am taking one example like metal 3. You can see here metal 2 and metal 3. Yellow color is the metal 2 and green color is the metal 3. Here you can see blue color, it is the metal 1. So what we used to do is we used to follow metal orientation. I'm taking M2 in a horizontal direction, M3 in vertical direction. If you do in this one means, if I fabrication, these two sit like so. Whatever the coupling capacitors that are going to form, that are going to be affect only this area. If you are not following the metal orientation means, if you fabricate it in this way, so here the coupling capacitors are going to form. Here, here we are going to see how the guarding is going to place. Here we can see how the guardings are going to place. Not only if any signals which are coming. Let's see. Let's see. Here IDC is the signal. You can see two signals are coming out. So in this way, the guardings are used to place. So by using these guardings, we can see how now the entire transistor is into product. So now nothing will happen to the original transistor because already the transistor is provided with the dummies and the guarding. So I think it is time up. So we need to close it. Sir, any queries regarding this? How to place guardings and how to use this?
Participants, it's over to you. If you have any questions, you can ask on this demo. Okay, if no more questions, we shall move towards closing this session. Srihar Rao, sir.
Yes, sir, please.
Sir, there are two questions in the chat. Are you able to see the chat or shall I read out?
Yeah, please read, sir.
Okay, I will read out. What is the, sir, first question, what is the significance of 2D materials in mixed IC designs?
Yeah, the 2D materials, of course, as I mentioned in the beginning, these advances are the kind of exploration, the research is not practical. Okay, so in the practical system design or the practical IC design, these technologies have not proved yet. Having said that, there are attempts to just try to make a sort of hybrid way of partially to some extent using 2D material and so on. But then as of now, there is no practical evidence of that usage in the system design or IC design. But hopefully, probably in future may, right? Yeah.
Okay, sir. One more question. Is neuromorphic computing IC comes under mixed signal IC, mixed IC?
Yeah, of course, neuromorphic. You see, that comes under mixed IC or not. The question is whenever you are basically extracting a signal which is sensitive in nature, and it requires analog efforts, and obviously you want to process in the digital domain. Therefore, you need to have digital counterpart, and therefore, definitely, it is a specific case of mixed signal IC design. Yes.
Okay, sir. Just now, one more question has been posted. What is the role of quantum electronics in mixed IC designs?
Again, these quantum electronics and these things, it also, as far as system design is concerned, it is to be proved, right? So it is a in future probably. Actually, it's more of it's related with the optical electronics, if at all. If the interconnection is through the light and all, then yes, But otherwise, as of now, in all the practical subsystems, of course, the quantum is still what to call it's only it's a guess only. Okay, it's not at all a reality.
Okay, sir. How do we choose the transistor sizing for gain, bandwidth, or power trade-offs, sir?
So transistor sizing, of course, the design itself is that, right? So if you want to design, for example, if you want to design a simple an operational amplifier is there, a two-stage op amp and all. You want to have the gain. So basically, as for the depending on the application, what is the gain required? Is it 75 dB or 80 dB or 85 dB or whatever? So depending upon the application requirement, you choose the gain first, and then of course the bandwidth also based on application as it demands. So is it meant for which kind of signals are supposed to be amplified? So that you have to see, and then you should see while choosing, you should be careful that you should not exceed. You should not exceed the minimum requirement bandwidth. Unnecessarily, you should not go for larger bandwidths because it unnecessarily invites the noise frequencies into the bandwidth, and therefore the system will be in trouble. And again, the gain and the bandwidth are sort of they try to contradict each other, and there should be very carefully one has to design. Because now you have to place the ports, adjust the ports, and do the compensation techniques properly so that the unity gain frequency is adjusted in an appropriate fashion. And this all is a design challenge. And the third one is a power one. Of course, power is whatever is the total VDD that's and the total bias and current, whatever the product is the power. So while designing, we keep power as the constraint, and then keep the bias current fixed from the power constraint. And within that bias current, we try to see what is the best possible. And also, slew rate is another. Actually, it's not mentioned. So slew rate is another specification we try to take into account. So
Yes, sir,
so therefore, keeping these constraints, we will try to fix up the design bias current, how much is required. And the bandwidth, of course, is also because the slew rate is I by C. So what is the capacitance, maximum capacitance that you're going to drive, that also plays role. So all these are how do you choose in the sense basically specifications are going to first dictate terms. Once specifications are dictating terms, then from that we try to choose what kind of technology is to be used to meet these specifications. And once you decide the technology, then within the technology, then what is required bias current to meet this slew rate specification, or otherwise, and then again, what kind of topology is required to meet this, whether single stage amplifier suffices or two-stage amplifier, or otherwise, what kind of and our cascode is required, right? So these things are to be decided. Once there are folded cascode, we can just use it. And also we have to just look at the noise specification as well, and process corners specification across the different process corners. What are the limitations? So within that you have to design. So there's always a trade-off between the gain, bandwidth, power dissipation, and so on. Certain things are in our hands. So but whatever is the ultimately the only one thing, one final point, we say that it's application. We should dance to the tune of the application's requirement. Within that application requirement, so we have to just trade between the amongst the various parameters.
Okay, sir. Thank you. Thank you very much. Sir, can you please switch on your camera that we will take a screenshot now?
Yeah. So actually, he has asked about the dimensions, right? So dimension, of course, that's what is the dimension in the sense. For example, you fix the bias current as a as 1 microampere or so. So the transistor is to be kept in saturation. ID is log mu C of W and VGS bands with the whole square, right? So you keep fixed V effective or VGS bands with the what is required to keep the transient saturation is you can anticipate, and based on that, you know the V effective or V span threshold, and you know what is the current, and therefore you can always, you know, mu C oxygen because it is specific technology, and all that required is WBL can calculate, right? So therefore, from the specifications, you try to just look at what is the current required, and then you try, or similarly from the bandwidth, for example, what is the GM required. So or from the gain, what the GM required, and so from these parameters, you try to just know from the equations and then try to evaluate the WBL. That's it.
Okay, sir. Thank you very much. Sir, can you please share the first slide of your PPT, just for
Yeah.
screenshot sake?
Yeah. Slide. I have to first share, right? Yeah.
Starting slide of your PPT.
I'll just go to that.
Arpita ma'am, please take one screenshot
Okay, sir.
after sir has shared the screen.
Okay, sir.
No, 1 minute. This is gone. Will they close it?
Yes, sir.
Okay,
Is it
sir.
okay?
It is. Yeah, it is visible, sir. Madam,
Sir. I'm taken, sir.
captured na?
Yes, sir.
Okay. Okay, sir. At the outset, let me thank you for spending your valuable time with a nice session. I know you are not in good health condition, but still you have accepted our request. First of all, let me thank you for that also. And it's already beyond time, sir. Let us close this session. Before closing, a few closing remarks from our co-coordinator.
Srihar Rao, sir, thank you, sir, for your wonderful session. Thank you for sharing your valuable insights with us. As we conclude the third day of our 6-day faculty development program, I would like to take a moment to express our sincere gratitude to all the participants for your active participation and engagement. A heartfelt thanks to the distinguished speakers for sharing their valuable insights with us. We hope today's sessions have sparked new ideas and perspectives that you can carry forward into your teaching and research practices. We look forward to seeing you again tomorrow for another day of learning. Until then, thank you once again. Thank you all.
Thank you,
Okay.
Arpita Garu, Professor Arpita Garu, and then Professor Srinivas.
Thank you.
Thank you, sir.
Thank
Thank
you,
you very
sir.
much once again.
Thank you.
Bye, sir. So, dear participants, you can leave the meeting. We are going to close the session.